Good morning, good afternoon, good evening, everyone around the globe. I hope you are staying safe at this special period. And welcome to this workshop at IV2020. It's called Internet of Things in Intelligent Transportation Systems, Opportunities and Challenges. And yeah, I'm bringing up this picture because we were supposed to meet over here in one of the casinos in the conference room, and after this is finished, maybe some of us will grab a drink or go to a buffet in some of the hotel, but unfortunately that's not going to happen. But since this is virtual, a good thing is you can join this meeting with a simple click, and we can meet virtually around the world. So it's a good and bad thing at the same time. I will quickly go through the introduction slides for around maybe 5 minutes, and then we can jump into each presentation one by one. And as I said in the email, in our calendar, in our website as well, the topics of this workshop will cover a wide range of IoT, and many of the talks are going to talk about digital twin. Some of the talks are going to cover Internet of Vehicles and connecting automated vehicles, traffic modeling, and cyber physical systems, and more topics. So it's a very exciting session, and organizations are coming from different entities, from academia as Harvard universities, Vanderbilt universities, University of Washington, UC Riverside, University of Iowa, UT Dallas, an industry leader from Toyota, and national lab leader from Oak Ridge National Lab. So they're all very exciting talks. Looking forward to that. And again, to reiterate of the goal of our workshop is to identify opportunities and challenges of the development of IoT, intelligent vehicle, and transportation systems. Especially right now, we have this concept of not just IoT. Many people are talking about AIoT, so AI plus IoT. How do we want to leverage those different technologies in the system of ITS as well as in intelligent vehicles systems? Again, another round of welcome from all our workshop organizers. Myself, Guoyan Wu from UC Riverside, Dr. Linshi Li from Indiana University, Purdue University, Indianapolis, IUPUI, Dr. Dongpu Cao from University of Waterloo, as well as Dr. Li Li from Tsinghua University. And I won't elaborate too much on the workshop speakers right now because I will give the introduction of each presenter before their presentation. And as I said, all 8 speakers, they come from different entities and cover a wide range of the research topics from different angles, from universities, from company, and from national lab. The workshop schedule for some details, and this is just a tentative schedule, and some might go a little bit over time, some might go a little bit short of time. That's fine. We can always adjust that. 2 presentations per hour. And last slide, so some instructions on the workshop. And I think all the presenters, they are automatically muted when they enter the chat, so that's good. And if anytime you want to raise a question by speaking that out, you can unmute yourself. And we always encourage to ask questions in the chat box as well to a specific speaker or in general. So if you want to ask a question in the chat box, please add the format to somebody at the beginning of your question, so it's easier for the person to track your question. So for example, if you want to ask me a question, so add to Ziran, or like add Ziran, what is the definition of digital twinning or research, things like that. And if you want to ask a question for the general, it's more like a kind of a semi-panel manner, so you can add to all. What is your vision for the impact of IoT on future vehicles? So for selected questions, I will pick them out and ask on your behalf to the speaker or to multiple speakers as a semi-panel kind of manner. And we also encourage real-time discussion among attendees as well. So you can discuss with each other for some of the topics in the chat box. And you know, based on the experience on one of our previous workshop in ITSC, you know, the real-time engagement among the attendees are very well delivered as well. We can have a lot of good comments and a lot of good thoughts coming out of those discussions. So last thing, follow the website for future updates. And as you can see from my window, I have already started recording for this session. So I will upload this right after this has been ended. And also send you an email to notify where that video is uploaded. So you can always trace back to one of the presentation and then you know, find the details over there. And I will also post some of, you know, the slides, and maybe we might have some special issue after this on some of the journals. So the call for a proposal or call for paper as well in either our workshop website or my personal website as well. So without further ado, let's go to the first presenter, as I said earlier, Yongkang Liu. So I think Yongkang is already joined here, and he sent me a pre-recorded video. So I will play his video, but he's online as well. So if you have any question, please feel free to ask him in the chat box, and he can answer in real time. And I can also pick out some of the questions after this presentation is finished. So let me do this intro for Yongkang. Give me 1 sec. So Mr. Yongkang Liu is currently a PhD candidate in electrical engineering at the University of Texas at Dallas, and was a visiting student at Nagoya University, Japan. He was also a research intern at Toyota Infotech Labs in Mountain View, California during 2020 spring. Mr. Liu's research interests include driver behavior analysis and intelligent vehicle advancement. Okay, let's get started.
So welcome everyone to my presentation. I'm Yongkang from the University of Texas at Dallas UT Drive Lab. And today my topic is fusion of camera and cloud digital twin information for intelligent vehicle. So for the outline, I will first briefly talk about the motivation of this research program, then go through the fusion framework, and I will talk about a user case and use that as an example to demonstrate our work. And finally, with conclusions and future works. So first of all, for the motivation, let me first give some background about digital twin. So the purpose of digital twin is to create a digital footprint of vehicle and driver. So they are able to provide cloud-based historical data to assist the analysis and prediction to ensure safe driving and provide some future services. So just like the figures shows here, the vehicle will upload the sensing and perception information to the cloud. Then the cloud-based algorithms could using such data along with those historical data to analyze vehicle and driver status. For example, assess driver's mental workload, or predict the maneuver of the driver is going to perform. Then it will send such information back to the driver, display it to drivers so they could make better and safe decisions. So here we focus on this last part, which is to how display the received information to drivers. So ideally, we would like to display all useful information as this example shows. We think this is the most intuitive way for drivers. For example, here is an overall score shows how safe if the driver followed this vehicle. And here is a probability of that vehicle's next maneuver. And here is the driver's status. So for some time, we want to display this information for every vehicle inside, but sometimes we only want to highlight one target vehicle because there is some imminent dangerous behavior. So a key issue here is how could we correctly overlay such information on the correct target vehicle? Or we could say the research problem is based on information from cloud system. For example, vehicle speed, GPS coordinate, and we want to match the correct target vehicle in the image. So we propose a sensor fusion framework using both camera and cloud information for this problem. So basically it contains 3 blocks as shown here: the coordinate transformation, object detection, and distance evaluation. So image taken by the camera will be used for object detection to generate all candidate bounding boxes, and target vehicle position information from the cloud and camera position will be used to generate the anchor point, which is used to determine the correct bounding boxes. In addition, depth image from that camera is used to obtain distance information, and this information is also used to determine the correct bounding boxes. So after the target vehicle box is determined, it will be used to visualize the received information from cloud. So the first part is coordinate transformation. So that is a 3D target vehicle location received from the cloud is transformed to a 2D point in the image plane. And that will help the identification of the target vehicle in later steps. So generally speaking, to transform a 3D world coordinate PW in this figure to a 2D image point PI here, 2 matrices will be involved. The first is extrinsic matrix. It will transform PW in world reference frame to PC in camera reference frame. So extrinsic matrix, they are the parameters used to identify the transformation between the camera reference frame and world reference frame. So it's still a 3D point, but after the transformation, the reference frame is changed. And the next is using intrinsic matrix to transform a 3D point PC to 2D point PI in this image plane. So the intrinsic matrix are the parameters of the camera itself, such as the focal length, lens distortion, and so on. So after this step, the 3D world point is transformed to a pixel coordinate. So for example, if the left vehicle is our target vehicle, and based on the location information from cloud and 2 matrices obtained by collaboration, we could draw this point on our image plane for later use. And the next part is object detection. So that is image taken by the camera will be used for object detection to generate all candidate bounding boxes. So 2D object detection is a well-studied problem in computer vision field, and it is not our intention to develop a new state-of-the-art object detection algorithm, so we just select YOLO for our implementation. So YOLO is a pretty popular object detection algorithm using deep neural network. It will make detection at 3 different scales, so it could perform better at detecting smaller objects and achieve relatively high accuracy with small latency, which is important for many driver assistance systems running in real time and have limited computation power. So the algorithm will output all bounding boxes locations is detected, and we will save this information for later use. So here, the anchor point was drawn from last step, and the object detection algorithm will give these two boxes. So intuitively, if a box contains the anchor point, then we will say that box will be our target box. So this has actually worked well for most simple scenarios, but here are some cases it failed. But for the left one, the object detection algorithm failed to detect the other vehicles here. And for the red one, both vehicles are successfully detected, but the anchor point is actually inside both bounding boxes. So to solve this problem, we could add in more anchor points, right? But what if we only have GPS location? What if we don't know other information, like vehicle dimensions? So another thought is using some additional features, which is our third part, that is using depth. So the depth image from depth camera will be used to obtain distance information, and this will compared with the true distance between eagle vehicle and target vehicle will help determine the correct box. So for cases like this, all vehicles inside are successfully detected, but the anchor point is inside both bounding boxes. So we could use the depth image taken at the same time and same angle, and that could help us get the distance from the detect area to the camera. So since we want the distance to be as accurate as possible, so we first redraw a smaller bounding boxes that will help avoid we select point not belonging to the vehicle, like to the road or to the background sky. Then we will randomly select a number of points inside this box, and we average it to get the distance. We then compare this distance with true distance calculated from eagle vehicle GPS and target vehicle GPS. So after compression, the box with minimum difference will be selected as our target box. So we were using Unity to build a simulation to test and evaluate our framework. So here shows an example. The cloud classified the driver in the right lane as aggressive driver. So it will send this information to our eagle vehicle. And after match to the correct target vehicle, this information is displayed to warning the driver. So the driver could choose reduce the speed to keep distance with the vehicle as a precaution to some potential dangerous behaviors. And we're also doing some post-processing assessment to test how well the matching method could pick up the correct target vehicle. So the left figure here, the baseline matching is the intuitive method, and the distance matching is using depth as additional information. So it clearly shows here the distance matching approach have better detection accuracy. But here I want to mention that the accuracy is also highly depends on which object detection algorithm we selected. And we also run the simulation as previous slides showed. We drove the vehicle manually, so we want to stay in its own lane, and we want to maintain a safety margin with others. So we compare the values of speed variance and time to collision in the red figure here. Also, the baseline is shown in blue, and the proposed model here is the orange one, which we displayed the information to the drivers. So we could say in general, lower speed variance and a larger time to collision could be observed, which means a safer driving behavior. So we could say the safety improvement by using our model could be clearly observed. And here I want to talk about a use case. So that is display the lane change prediction information from the cloud. So here from the physical world, the Eagle vehicle will upload the perception information such as speed, location, so on. And the cloud algorithm will doing lane change prediction. So this is another work from our colleagues, and he will also talk about this in detail later. And after we got the probability of lane change, we want to show in this probability here to display it for the drivers. So here, as an example, we think driver is more sensitive to the colors than the numbers, so we also use color code. For example, here is green, means there is a low risk of lane change, and red means there are a higher chance of lane change. So as the video shows here, So as the video shows here, if there is a low probability of lane change, then the Eagle vehicle's driver could pass this vehicle confidently. And if there is a high probability of lane change, the driver may decide to lower their speed, or they could also decide to just change to another lane, as shown here. So in the end, to conclusion, in this work, we built a sensor fusion method for camera and cloud digital twin information. We implement this driver visual guidance system in Unity simulation and showing the safety benefit of the proposed system. And for future works, one direction is to improve the system overall accuracy, and the other one is to consider real-world implementation. So that will be all of my presentation today, and thank you for listening, and I'm open to any questions. Thanks.
Thank you, Yongkang, for this presentation. I think, yeah, 2 questions remaining in the chat box, and thank you for Lingxi and Chris to raise a question as well. So Yongkang, maybe I'll just ask you these 2 questions during our conversation. The first question is, what variables do you use for lane change prediction?
So can you hear me well?
Yes.
Okay. Yeah, so for the lane change prediction, we were actually using information such as the vehicle distance from to others and their vehicle speed, this kind of information for lane change prediction.
Mm-hmm. Can you maybe elaborate a little bit on the model of the lane change prediction? What kind of model you use for that?
I think it's I cannot remember the details correctly, but I think we were trying to using some multi-layer perception model for this, right?
Okay. The second question is, which simulation platform did you use? Is it Carla or something else?
We use Unity to the simulation.
Okay. Yeah, thank you. I think that's all so far. So for all those attendees, if you have any other questions, please feel free to ask Yongkang in the chat box, and he can always answer that later. Thank you, Yongkang.
Okay, thank you.
Chris, are you there?
Here, present.
Yeah. Great. I can hear you. So you can start to share your screen, and meanwhile, I can do the intro for you. So our next presenter is going to be Chris Schwartz. Dr. Schwartz received the bachelor degree from UIUC in 1990 and the PhD degree from the University of Iowa in 1998, both in electrical and computer engineering. From 1998 to present day, he has been a research engineer at the National Advanced Driving Simulator at the University of Iowa and is currently the Director of Engineering Modeling Research. His research has involved all types of advanced driver assistance systems, connected vehicles, warning systems, automated vehicles, and driver impairment modeling. Dr. Schwartz's current research interests include vehicle automation and distributed simulation. He is a member of ACE and a senior member of IEEE. He serves on the ACE On-Road Autonomous Driving Simulation Task Force, as well as the TRB Committee on Vehicle Highway Automation. Yeah, Chris, you can go ahead.
All right, thank you, Ziran. And thank you, organizers, for inviting me. And thank you, everyone who's attending. It's good to be with you, even if it is only virtually. I'm going to talk today about a title that is Digital Twins from Macro to Micro, and I'll explain exactly what I mean by that. But the outline, basically, my talk will be a little bit of background, just a touch on digital twins and what came before digital twins. And then I'm going to cover 3 projects that we've done at the NADS, or are doing, that cover different areas, but there's a thread running through them, and that is their potential application for a digital twin. And after I talk about those 3 projects, I will talk about some of the challenges and opportunities that I see that are sort of exposed by these projects that, that I'm going to review. And then I'll move from that into a vision for a rural digital twin that builds off of the work we're doing on road around Iowa City, and conclude and hopefully have plenty of time for questions after that. So digital twins, you're going to hear a lot today about the cyber-physical element of digital twins, and it's very exciting development. It is in many ways an evolution of digital environments and simulation that have come in the decades really prior to this. The connection to the cloud is basically moving us from, you know, an era of small data into an era of big data. And the idea of parallel driving, which I'll talk more about, make the connection to our research, you know, has to do with really modeling some of the invisible aspects of driving that fall beneath the surface of the more obvious and visible aspects of driving. For instance, the cognitive aspects of the driver, or cognitive, if you want to say, thinking aspects of the artificial automated vehicle. Well, I'm going to very quickly pull you now from this macro modern idea into a more micro world. And you can think of macro maybe as being the big data and micro as small data. You could think of macro as being many actors in the simulation, and micro being few. However you want to think about it, that's sort of what I mean. And as we go back in time, we used to call this, you know, many different terms. Back when I started in the 90s, this was virtual proving grounds. And we did a lot of work on creating virtual proving grounds that combined the driver, the vehicle, and the environment into a simulation, and in our case, simulator environment, where the vehicle was modeled, the environment was modeled, and then the driver was put into that context. Of course, as time went on, we became better and better at modeling the driver too. And to a large extent, in a significant way, that's what we do with automated vehicles, is we ask them to model what a driver would do. But these VPGs were very useful for designing systems, testing, and acquiring, which simulation-based acquisition is a big term in sort of the defense and military world. Okay, so we also talked about some other terms in our history, like geospecific scenery databases. A lot of the things that we develop and have developed over the last 25, 30 years can be classified really into these geospecific databases and geotypical databases. You see an example here of a model of downtown Iowa City that we did for a project. And this would be something that could be used as a digital twin. A lot of the work that we do just uses this geotypical database, which is just meant to represent the Midwest or something, a highway, but doesn't match the real world necessarily. So we have all these different terms that we've used in our history, virtual proving grounds, geotypical, geospecific, but they've all been sort of leading us in this direction. Okay, so 3 projects I promised to talk about. The first one is called Automated Driving Systems for Rural America. And this is a project that was fairly recently awarded by US DOT. And we are getting started, but it's gonna run for the next 2.5 years or so. Why are we doing this project? Well, the benefits of automated vehicles are there are many, but in the safety aspect, we expect to see automated vehicles reduce and even eliminate all of these driver-based crashes, which make up 93, 94% of all fatalities. So this first statistic is a bit striking. And even though only 19% of Americans live in rural areas, nearly half of traffic fatalities occur on rural roads. So if we're serious about attacking this fatality statistic with automated vehicles and intelligent transportation systems, we must bring them onto rural roads. However, rural roads have unique challenges, as we all know. They have outdated designs, poor paving and marking, limited line of sight. They have shoulder drop-offs. There are animals that wander around, and the weather effects can be severe, not just during the weather, but after the weather. After a rough winter, a road that you see there would be just trashed and, you know, have ruts in it perhaps. And so it can be quite serious. So what we're doing in this study is we're acquiring a transit van, which we actually just took delivery of a couple weeks ago, and we're instrumenting it and automating it. And that van is going to take on passengers, and we're going to be shuttling them around a rural route south of Iowa City and collecting extensive data from all of the automated sensors, from the CAN system, from the camera, from the Mobileye system. We will be mapping this route, creating an HD map. We will also be administering some questionnaire and physiological data for the occupants and the safety driver. And most of this data is going to be publicly available. And we're going to host that data for probably 5 years after the end of the study. So this is a really great opportunity to collect a lot of this data in a rural environment. All right, next study. The effects of adaptive headlamp features on driver responses to pedestrians and bicyclists. This is a NADS-1 study that was funded by Toyota CSRC, nighttime environment specifically, trying to address some of the pedestrian fatalities that have been going up and up in recent years and reached their highest numbers since 1990, just a few years ago. More than half of these pedestrian fatalities happen when it's dark outside. However, new headlamp technology, LEDs, digital micromirror devices are making possible new smart adaptive headlamp systems. So there are great opportunities here. And so what we did in collaboration with Toyota was to come up with a conceptual advanced headlamp system that uses a spotlight that can shine a light onto this vulnerable road user, a pedestrian or a bicyclist, a brightening headlamp feature that makes the dim, these headlamps are all on dim for this feature, and then they become brighter, and hopefully that's noticeable also by this pedestrian or by the bicyclist. And then an icon that you can actually paint on the road. And if you've seen videos of this, it's really amazing. You can use these headlights, these new headlights, almost like digital projectors, and paint pictures on the road. And then this system had two phases, a caution and a warning phase. So we implemented this and did all kinds of experiments. By the way, I should mention that while we did experiments on the NADS-1 from the perspective of the driver, our colleagues over in the Hank Lab on Iowa's campus used their pedestrian simulator and bike simulators to do similar, the same experiments from the perspective of the pedestrian and the bicyclist. So we wanted to see what the benefits were for the driver of this system and also for the pedestrian, for the bicyclist. So we came up with these 6 different events, crossings and overtakings. And here's some video that shows you an example of a bicycle crossing the road. You can see that one kind of comes out of the dark. This is with traditional headlights. And then the next one I'll show you has the spotlight. And notice how the spotlight illuminates that bike before it even enters really the illumination of the headlights, increasing the conspicuity of that bicycle a great deal. And then the third one I'll show adds in the brightening feature. So watch for the area of the headlight to get larger and brighter, and then it'll snap back to normal. And we hope that a bicyclist might detect that, or that it might create the illusion that a vehicle is coming faster or something. We don't really know what the effect of that might be. That's why we're doing these experiments. And then the icon, I'm not showing a video of the icon because in the video, it just doesn't show up well. I mean, the pedestrian can see it, the bicyclist can see it, but they're kind of far away and it just doesn't show up in the video. So I can't show a good video of that. Third study, developing connected simulation to study interactions between drivers, pedestrians, and bicyclists. And this was a study recently concluded, funded by US DOT Federal Highway. And there's some similarities with this one and the last one. Pedestrian fatalities, it's concerned with pedestrian fatalities, of course, but also multiple vehicle crashes, of which there were almost 12,000 in 2016. And the thing that these two statistics have in common is that they're concerned with the interactions between road users. And we've studied driving pedestrian and bicyclists using simulators for many years, many decades in crash scenarios, and they're wonderful tools. But the limitation is that they don't capture the interactions truly among these road users, because one of those users typically is controlled by a computer. So we'd like to be able to do that. We'd like to be able to study real interactions between road users. And to do so, though, makes everything a little bit more complicated. Makes the experimental design more complicated, makes the analysis more complicated. Nevertheless, a worthy thing to do, we felt. So we developed an architecture to include the driving simulator, pedestrian simulator, bicycle simulator, mini sim, and scenario traffic into a common environment and designed a little database and used that to run a little data collection. And importantly, the feature that we added here was the ability to create avatars for the pedestrian or the bicyclist and also for the driver inside the vehicle, so that those avatars, you could see each other's avatars and you could look and you could gesture. So here's what that technology looks like. On the right, you can see a grad student, Shomo, who's wearing a headset. And on the left, you can see the driver in the NAS1. And I don't know if you can see my mouse, but I'm circling the avatar for that pedestrian. So the driver can see the pedestrian is seeing the same virtual world, sees that red car, sees the driver's car, and you can see he's waving now and saying, I give you permission to drive, I'm not gonna cross. And so then the driver shifts into gear and drives forward. So there's an example of some good interaction. But what's really interesting is to then see this with some novice participants. So we did a small proof of concept data collection. We had 14 pairs of drivers and pedestrian. So here's an interaction between a driver and a pedestrian avatar. So there's a real person behind this pedestrian, and you can see some good gesturing going on. Now this pedestrian turns around and he's like, okay, cross again. In the real world, pedestrians don't just walk back and forth across the street over and over again, but they kind of did that in this study a little bit. Now here's a agent-controlled or computer-controlled pedestrian. Look at the differences in the behaviors. Now this is not bad animation. This is pretty good animation of a pedestrian, but there's no looking, no turning of the head. There's no indication that there's interaction at all. So here's another driver. That's a computer controlled avatar. Again, no interaction really whatsoever. And then here's an interaction between the driver and a human controlled avatar of a pedestrian. Now this pedestrian turns around, looks like, oh, they want to go. And the driver did a flurry of foot movements from their brake to their gas, like she wanted to go, but she ended up stopping. And now here's the same thing from the point of view of some of the pedestrians. They're able to see the same world, and they wear trackers on their wrists, on their ankles, and one you can see on the back of the waist. So that's 1, 2, 3, 4, 5 trackers. And then the HMD also counts as a tracker. This is the Vive Pro. So you can see in the background, there's a base station. Vive needs base stations to do the tracking. So with these 5, 6 trackers, we can do inverse kinematics, create the avatar, render it in the scene, and that's how we're able to generate avatars. It was actually a very complicated procedure, and there's a lot more that went into it, but I won't get into the gory details today. So here's another pedestrian walking very carefully across the road and then giving a wave to the driver, I think. There you go. Like, who's gonna go? Like, what did that wave mean? It looked like he wanted to walk. All right. So these 3 studies bring to mind several challenges and opportunities, and a lot of them come from this automated driving study that we're doing in a rural environment. But then some of the opportunities, I think, really come from these examples of interactions that I've showed. Obviously, we know that weather is a challenge and remains a challenge, and seasons remain a challenge. So I'm just pointing it out. I'm just pointing it out because we've got to get out of the lovely environments of Arizona and California into the wonderful all-season environments of Iowa and Michigan and the Midwest. And you can see this road here is a rural type of a road. So even without the weather, without the winter season, it's got all the challenges of the lane lines missing and not well-defined road width and all of this kind of stuff. And like, is it a one-way? Is it a two-way? What's going on there? Digital environments just need to keep improving in order to encompass these types of driving situations. Now, here's an example of, all right, the consequence of that is when you increase the fidelity of your environments and make them more complex and challenging, you've got to also raise your game in other areas. And so this is showing an example of a high fidelity multi-body vehicle dynamics. We use this type of multi-body dynamics at the NADS. It's one of the things that, Iowa was very famous for a long time. And this particular example is coming from Project Chrono, which our colleagues up at University of Wisconsin work on, along with another team at University of Parma. So they're doing fantastic work on high fidelity vehicle dynamics. And I think that these are going to be critical to operate in the more challenging environments at the extreme edges of their performance, okay? And then these two challenges now brings up a whole nother challenge, which is the verification and validation of these simulation environments. We know that V&V is a challenge for simulation already. Every simulation tool that you put into the mix sort of needs to be validated on its own to know that you actually have trust in that tool. And now I'm proposing to make the visual environment more complex, to make the vehicle model more complex. That vehicle model may go from having tens of parameters to having hundreds of parameters. Big challenge. One more challenge I'll point out. We're going to need to move from an environment of sensor simulation that says, oh, I can model a LiDAR, I can model a radar, I can model a camera, to one which says that, well, is your LiDAR model modeling a Luminar or a Velodyne or an IBO? What exactly are the characteristics there? And how does each one differ? And are they validated models that we can use for a particular manufacturer of vehicle? So all of these things are ways that VPGs need to evolve into digital twins and need to evolve further and further. And they take more processing power, they take more, they just take more work. All right, so now I'm getting to a point where I'll start to try to take you back from the micro up to the macro, if I do my job anyway. I'll try to do my job. So my vision for a rural all-season digital twin would look something like this. We're doing this great study, from USDOT, where we're collecting all this data on a rural environment. So we should go ahead and model that environment using the data that we're gathering, the HD map that we're creating, in order to have a digital twin and VPG capability. The sensor data, we are collecting this data all throughout the year, day and night, all 4 seasons. So we should be able to come up with good models. I don't know how important it is to differentiate summer from spring, but capturing those winter conditions certainly will be very important. Not just because there's snow on the road, but there's no leaves on the trees, and the whole picture of the environment is going to look different. Then integrate their good sensor simulations, at least state-of-the-art phenomenological sensor simulations into this, to enable full simulations of automated driving systems and validate those simulation results against the real-world sensor data. And then at that point, now we have something that we can use for research and development. We can either use it in a macro case to run millions of miles and test edge cases and communicate to the cloud and have a cloud-based digital map, or we can use this environment to do road user interactions, as I've discussed, and run it. We can run this over multiple times with different sensors and improved sensor modeling. So there's a lot of foundational research that continues to need to be done to add fidelity. And what I'm arguing here is really that these rural environments are more challenging and they require a greater degree of fidelity, okay? But what I'm also saying is that, well, let me go to the next slide to discuss this now. Here it is all in one slide for you, macro to micro, but let me work my way back up from micro to macro. I've talked about how important it is that we study road user interactions and driver behavior. You know, we learn things about how real people behave, and those types of models that we can create from that have been used in previous, you know, in the past. For example, in macro traffic simulations, to start to introduce heterogeneity into those models, right? You don't want to have 1 million cars in a traffic simulation that behave all the same way. You'd rather have a heterogeneous population in which different types of drivers drive differently. You have aggressive, you have conservative. You can't really make those kinds of models without doing the micro kind of work that I've discussed today. And so when you think about the parallel driving aspect of digital twins, you're really trying to capture that invisible layer, the cognitive layer. And that can be captured if you really study some of this micro simulations that I'm doing here. But if you do it on the digital twin environment, then you know you've got a better shot at generalizing those results to the environment that you're actually running in. Okay, it's a challenge always to generalize, to know when and how you can generalize simulation results into the real world. Helps a lot if you just have the same digital twin to work with. High fidelity models, and then moving back up to the macro layer, the big data layer, we can start to run these millions of miles and edge cases and get confidence that you have a system that accurately represents the physical system that you're dealing with. And yeah, I think that's probably the whole message. So I think I'll just stop there and see what kind of questions we have. Thank you so much for your time and your attention.
Thank you, Chris. Thank you very much for a very interesting talk. Maybe before diving into details, I have a general question for you, and which came from a person that when I advertised this workshop as well as the other workshop, a person asked me the fidelity issue of simulation, or this kind of digital twin or IoT that we want to simulate the real world, but it's not real world. There are many cases that in the real world that we cannot like simulate in the virtual environment, and the person he insisted that the simulation doesn't make that much sense to allow your algorithm to be able to run in the real environment. So I was running out of my answers to that person. So what's your answer to that question?
It certainly is a valid question and a viewpoint that needs to be considered, thought about. But I mean, just on the surface of it, I'll start by saying that if you don't think that simulation is viable, then you don't think that digital twins are viable in some sense. So just think about the last few years of what we have achieved with computers and GPUs and what that has allowed us to do with the visual rendering. It's just been amazing how we can, you know, almost photorealistically render a scene, an environment, and use that to simulate sensors and camera inputs. Now, nobody can really deny that because it's been so obvious over the last few years what kinds of improvements have been made. And what I'm suggesting is that we need to devote some of that attention that the visual environment's been getting to other areas of the simulation, for instance, vehicle dynamics. A lot of people would run something like a PhysX model, which is great for what it is, and it's great if you're on a highway, but it's basically a box on springs, and so moving to something like a multi-body model gets you a lot closer to that realism. It does chew up some more CPU cycles. It's a little bit more complex to run, but well within our ability to do in real time. And we're very close, to being able to run sensor simulations and everything like that in real time below the surface. So the fidelity needs to continue to increase, and the computing power will come along to meet those needs. Now the question is validation. So really that's the last piece. And we all need to do our due diligence, and a lot of work needs to be put into validating these simulations. We can't take that for granted. So from my perspective though, I think it's very possible.
Thank you. Thank you. Yeah, maybe I get my answer to that person as well. Thank you. For two detailed questions, one from Yong Kam. So I think for one of your study, you showed a vehicle to pedestrian kind of thing. So how do you know the presence of bicycle and pedestrians in that simulation or in that scenario? Is it through V2V or something similar to that?
Yeah, thank you. In that study that we did, there was no V2V or automation sensors in play. It was a visual ADAS system. Visual meaning the ADAS component came through the headlights. So that was an ADAS system for the driver. By manipulating the features of the headlights, the goal was to try to make that bicyclist or pedestrian more conspicuous to the driver, and vice versa, to make the driver, the approaching vehicle, more conspicuous to the pedestrian or to the bicyclist. So there was no V2V element in that study.
Understood. And the other question is from Si Yang. So what is the degree of freedom of the driving simulator, and what's the software for scenario building that you are using? I guess from my perspective, it's multiple software, right?
Yeah, we used lots of different softwares. Most of them were developed in-house. Our simulator goes back, over 20 years now. So what you see pictured on my screen here, the NAS1 motion base, it's 13 degrees of freedom. It's got a hexapod, a turntable on top of that, a large XY system with belts, and then 4 vibration actuators inside the dome to add high frequency vertical vibration to the vehicle. So you get road feel. So that's 13 degrees of freedom. I think I forgot the second part of the question.
So what kind of software for the scenario building?
Yeah, thank you. We use an in-house developed software called ISAT. It's a scenario authoring tool. It's a GUI. It's a graphical-based user interface to drag and drop elements of a simulation or a scenario, like triggers, to make the computer-controlled vehicles behave a certain way, to make things happen when we want them to happen. So all of that stuff right now is really developed in-house. And one of the challenges that we have moving into the future is starting to adapt to what are becoming the industry standards, right? Things like OpenDrive, the tools that people are using like Carla and Unity. But those are things that can be done. We can write, converters to change a road network from one format to another. like those are not huge challenges, but we've got to do them, I think.
Thank you, Chris. And I think there are 3 more questions. So for the sake of time, maybe Chris, you can answer them in the chat box and discuss with them in details. Thank you, Chris, for your time.
Thank you.
And by the way, thank you, Henry, Sheriff, and Boyan to raise the questions. So please talk with Chris in the chat box. So Remy, I saw you over there, right? Can you unmute yourself?
I'm about to unmute.
Yeah. So you can go ahead and share your screen, and I can do the intro. So our next presenter is going to be Remy Ke. Mr. Ke is a PhD candidate in Intelligent Transportation Systems and also a manager of the Smart Transportation Applications and Research Lab at the University of Washington. He received his bachelor's degree in automation at Tsinghua University in 2014 and his master's degree in civil engineering at the University of Washington in 2016. His research has contributed to the fields of smart mobility, traffic sensing technology, automated vehicles, artificial intelligence in transportation, and the Internet of Things. He is a member of the Data and Information Management Committee of TRB and a young member of the Infrastructure Systems Committee of ASCE. He also served as the chair of Student Affairs at CODA from 2016 to 2020. Recently, Mr. Ke received the 2019 Michael Kite Outstanding Student of the Year Award presented by the USDOT Region 10 University Transportation Center. Yeah, Remy, you can go ahead.
Yeah, sure. Thanks a lot, Ziran. It's nice to meet you and everybody. I saw some old friends in the participant list. So today I'm going to talk about the design and some field implementation of the IoT systems with the video analytics ability. So like Ziran just mentioned, there's somebody raising doubt about like simulation, the fidelity issues. But I think simulation is like a master step. So we have to do simulation first. But also I think the field implementation is another required step for any like intelligent transportation systems applications. So probably a lot of people know that Elon Musk mentioned like anyone relying on LiDAR is doomed. This is under the context of autonomous driving. So some people think using just cameras and some basic sensors, we can achieve autonomous driving without the LiDAR sensor, which is advanced but more expensive. But so we're not saying this is true or false, but this is a point that we may achieve autonomous driving and some very advanced functions using just the cameras. So, you know, people driving with 2 eyes, basically 2 very advanced cameras, like without the like LiDAR sensors. So the camera and video analytics, they do have generated a lot of interest in the intelligent transportation field. So let's look at, so we know that the video analytics for ITS, there's a lot of existing cameras already, surveillance cameras, like all over the traffic network, and sometimes there's over 10 cameras at one intersection. And you know, for a lot of people's their own personal car and the public transit, there's like dash cam and other cameras. So camera, they have relatively low cost and they are widely deployed, and also they contains rich information. They're just a different type of data structure. So like a 2D array and a combination of them, so the frames and combined into videos. So there's a lot of potential for using cameras for doing research and application for IoT and like traffic surveillance, autonomous driving, those things. But you know, this paper like recently published in the journal Computer, it mentioned in the IoT or edge computing context, the real-time video analytics is considered the killer app So as we mentioned, the videos, they are specific type of data structure, like with a very large volume. So in a lot of IoT cases, the network is unreliable. So to streaming those videos in real time to the cloud requires very low latency and large bandwidth, but that's not the case for many places and also for the video data structure. And another thing is, we know to process videos, we require a very high computational cost, especially considering if we incorporate the latest AI technologies into the IoT systems. So those are the concerns, but we do want real-time video analytics for like many applications. We don't want to do post-analysis, which may have limitations in many perspectives. So the objective, I think the research objective for real-time video analytics in the like IoT and ITS, I think we have to address them from so both the algorithm side and the system architecture side. So we need to design those algorithms and system architecture to address those problems. And we have to focus on both the design and field implementation to make sure a system works. And also in the application, there's, the vehicle side, the infrastructure side. We will focus on both the infrastructure application and also intelligent vehicles. So we talk about V2X communication. So there's always vehicle and infrastructure are the two major components. So in this talk, I will introduce two examples of our lab's recent work in IoT with real-time video analytics. So the first example you see here, it's about on the smart infrastructure side with a smart parking surveillance system. So we conducted the study in fall 2018, about 2 years ago. So we installed the parking surveillance system in the Angle Lake parking garage. That's a very big garage near the Seattle Tacoma international airport. A lot of people use that parking garage as a park and ride space for their everyday commute. But for the large parking garage, the real-time parking information, the occupancy, those things are always very important. So we tried to develop a multi-sensor system to monitor the parking spaces with IoT a platform, so the Raspberry Pi 3. So here I will mainly introduce the camera part. So another sensor part is not the focus here today. So we conducted a study on both the 3rd floor and the 6th floor. So 2 cameras monitoring 16 spaces. You can see the picture here. The 6th floor is the top floor with the outdoor thing, and 3rd floor is the indoor thing. So here, this is the overview of the system architecture. So we try to split the computational cost to both the edge devices, so the Raspberry Pi, and also the server. So we conducted the detection tasks on the Raspberry Pi, the IoT devices, and we just transmit a very small amount of information, so some intermediate processing results from the IoT device to the cloud server. And then we do some tracking and occupancy judgment algorithm on the server side, try to get the parking occupancy information. in real time. So there's like basically two vehicle detection algorithms on the IoT side. There's a AI-based single-shot multi-box detector with a mobile net as a backbone. And so that's the AI detector, but that cannot operate in real time on the Raspberry Pi. You know, so we have another like more traditional background subtraction modeling method on the edge for the vehicle detection that can operate in real time. So we do both detection on the IoT device, trying to get like information that we can use for the parking occupancy. So this is the, first of all, we do a transfer learning on a MyoTCD dataset for the SSD detector. So this dataset, you can find it online. And so it's like traffic surveillance dataset with over 100K images, all from the surveillance cameras in challenging scenarios. So we like do some like fine tuning of the network using this dataset and to improve it for the detection performance. And here's an example. You can see like some like very small objects and some cars blocked it by the trees, and in the nighttime with some occlusion. Those can all be like detected appropriately after the transfer learning on the MyoTCD dataset. And for implementation on the IoT device, we use TensorFlow Lite. So that's kind of like an optimization library, which like you can apply it on the TensorFlow inference graph, and they can do optimization, quantization to speed up the detection performance. And we mentioned there's another like real-time detection, like the background detection method. It's more traditional method, but since it's in real time, so we combine this information with the SSD detector information, and we got both the detected results, just some lists to the server, and we process those data instead of streaming all the videos to the server. And also, you know, the data volume is limited because there's no Wi-Fi and those network in the parking garage, and we use a kind of like a 4G network with limited data volume monthly. So that also saves a lot of the data volume and bandwidth. And on the server side, with the detection results, we modified a tracking method, which is the sort method, so the simple online real-time tracking on the server a little bit to improve the performance. Because this method, it just takes the bounding boxes information without those deep features needed. So that's proper for our application, and to use the boxes and other data from the IoT device. And we also developed another, so some occupancy judgment algorithms on the server. So to enhance the reliability, you know, there's always extreme conditions, bad weather, and nighttime, and sometimes occlusion, like given the camera angle, and sometimes the large vehicles like trucks. And we found that the more traditional algorithm, it operates like relatively stable in those extreme conditions. So we did some study and built an algorithm to combine the two detection results and to address those extreme lighting conditions and occlusion issues. And over the like 3 months testing period in the Sun Transit parking, the Angle Lake parking garage. The overall detection performance is very good with one camera monitoring multiple spaces. But note that still in some like strong fog like conditions and some sunny conditions with like direct sunshine to the camera, the detection is relatively like has lower accuracy. But overall, it achieves over 95% accuracy. So here are some examples you can see like on the 6th floor, the outdoor conditions, and you can see the cloudy and raining condition performs very well. Like except sometimes in the rainy condition, there's raindrops on the camera lens, and in that case, there's no way to detect those parking spaces. But most of the cases, because the camera is waterproof and there's no raindrops, and it performs very well. But you can see in some like morning, like direct sunshine and some very strong foggy conditions, the detection is relatively lower. But those boxes suggested the SSD detection results, and the final detection results is on the top with the red and white circles. So you see the performance is improved with our algorithm and system architecture. So there's also occlusion cases like the last image. You can see this large van block space behind it, but we can still detect the vehicle like with the tracking and the background algorithm. And we compared, it's kind of like a like qualitative comparison with the state of the arts, and we found there's like advantages in the like how we use the computation platform, the system architecture, the real-time operation, and also the testing in different scenarios and system efficiency. Yeah, you can find more details in our paper, like showing here below. So that's one example study we conducted on the infrastructure side. And another study I want to talk about today is the application of IoT in the intelligent vehicle field. So this is a study like still ongoing, like funded by the Federal Transit Administration. So in this study, we use more advanced IoT device, which is the NVIDIA Jetson TX2 device. So we try to evaluate some other like collision avoidance technologies with autonomous braking ability on buses. So we build this platform for real-time like data fusion collection and also video collection so that we can verify the event warning caution cases for the commercial system. And also another objective or application of this system or the study is that we can collect the near crash cases or the it's kind of a major source for the corner case for the automated vehicle testing. We know like currently the automated vehicle, they can like handle most of the cases they encounter, but we just need more corner cases for training and testing. So we try to use this system as a like standalone and a low cost platform for corner case collection. And I guess most people here, we know about what's a near crash and why we use near crash data. So just to mention it a little bit here, we know if we want to study like traffic safety of an intersection or some scenario, we want to collect some collision data, but collision data is usually very rare. So like sometimes maybe in 5 years, there's only like 10 collision. So we cannot conduct like very solid statistical analysis using the collision data. So people consider using the near crash or near miss data as a surrogate safety measure for those kind of safety studies. So like many people have done like work in collecting the near crash data. That's the near crash data. And let's talk about this project again. So this is the Pierce transit buses we are installing our systems on. And you can see on the right picture, this is a LiDAR system we are evaluating. They have like 3 LiDARs for like collision avoidance and detection. And we are trying to evaluate. So before installing our system on the buses, we tested the system in the like some cars, basically our personal vehicles first, before officially installing them on the buses. So you see, I put a dash cam and like power inverter and the NVIDIA device and some GPS modules. So in my own car and drive it around so for some time, so to collect the data. So here's the software flow diagram for this on the system. So the cool thing here is, you know, we with the like AI-based detection results, there's some bounding boxes, and we modeled those bounding boxes. We played with it, and we found it's very useful information. And with some camera model and some new algorithms, we found that we can use the bounding boxes generated by the deep learning detector and tracking results to get the TTC, the time to collision, and some like horizontal motion, longitudinal motion information from just the single camera with the like deep learning detection results. And we developed some rules, some identification, like pattern identification rules for the near crash. And actually, you know, the detection, so on the camera is free of the intrinsic camera parameters. So that means we don't need to know the like what's the focal length of the camera, and so that we can still get the time to collision values. And this is just the flow diagram for the local test on my personal car with 3 different threads, the frame rating threads to address the latency issue, and data collection threads when there's an event. It's like a single thread, a separate thread. And on the bus testing, because we need to communicate with the LiDAR system, so there's 2 other threads not shown here for the CANs and message sending and receiving. So we send a like a trigger via the CAN network to the LiDAR, and we also receive 0 trigger in real time, so that we can collect the videos needed for evaluation. And so, as I mentioned, we use TensorFlow Lite for the optimization on Raspberry Pi. But here on NVIDIA, they have like TensorRT SDK with TensorFlow. You can do the quantization on the inference graph and improve the performance so that we can do the real-time like detection. That's one thing. But here I forgot to mention. So we're modeling the bounding boxes with like some very simple like linear regression complexity method. So that also helps a lot for the real-time operation. Otherwise, cannot do it in real time. And so I think given the time, maybe I just quickly go over this slide. So this is for the near crash detection algorithm. So first we want to understand the what a near crash look like in the camera view, because that's a 2D view instead of the real world 3D view. So we cannot get the TTC or PET or some other indicators very easily from just the 2D camera view. So we have to understand the camera model, like how the near crash look like. So if it's going like directly vertically down to the bottom of the camera view, and we consider so that's the relative motion like has a potential to develop into a collision, and we model the object the size. If it's a decrease, it's moving away. If it's the same size, stay at the same distance. And if the size increase, it means the relative motion is towards the ego vehicle. So that's some basis for the detection. And here you can see this is some picture we took for the installation and testing on the Pierce Transit Bus 233. And you see the device and some of the CAN adapter, and those are all installed in the radio boxes. But those are not all our devices. Some are the original, some previous device in the bus. And we did some installation in August, and here are some system components. And we also developed the auto power on module, because the media adjacent you cannot boot up automatically, but you don't want to push the start button every time the bus start off. So we use a Arduino board, although it's overkill, but we use it for the auto boot up. And here's some data we collected like from the different systems, and also we sample some random events in case to check if there's any false negatives. And here's a short video I uploaded. And you can see the detection when there's a near crash detected. Here for demonstration, we use a red box instead of a regular green box for the detection. So here I also want to mention that we did not really do a lot of, for this video, like the transfer learning, the fine tuning with some specific data sets. This is just the based on the COCO data set, some pre-trained network. But you can see the detection of the near miss still pretty good. Yeah, let's go quickly. And this is like I use my phone when I'm driving and to show the real-time detection. And this is like on the bus. We have the
we got it. We got it.
Yeah, and here I'm showing some other results. So the driving, like the GPS trajectory, and 2 near crash events detected on the UW campus. That's the like before the installation with my own car. And those are the 2 projects like for the IoT field implementation, how we design some system architecture and algorithms. And just want to mention another ongoing project. We are collaborating with the Norwegian Public Road Administration. There's a mobile unit for sensing traffic. This device we are developing it for the road surface condition detection, the traffic volume detection, visibility detection, with like there's AI trigger method here. And thanks for your time and attention, and thanks the organizers for inviting me and to introduce our work again. Thanks a lot.
Thank you, Ramin, very much for very fruitful discussion and this presentation. Maybe to start off, I have a question regarding the first part of your research. That was very interesting regarding the parking lot.
Sure.
So you install that camera on the infrastructure, or maybe on some places you mount it high, and so it can overlook the whole area. And the algorithm running inside, can that be migrated to other scenarios? Like if you put it in an intersection and then monitor vehicles coming from different ways, or the algorithm that you developed for that application, it's just fixed. It's just for detecting the parking spots.
Yeah, that's a good question. So, I mean, for that specific system, that's for parking surveillance, but we can modify the algorithms, like kind of, we can do it in a short time to modify it for some other similar applications, like monitoring traffic at intersections or roadways. So the last thing I mentioned, so here we have a traffic volume detection, and this is based on a similar detector and structure with the parking.
So pretty much it's the same like IoT system architecture, but just running different algorithms, right?
Yes, yes.
I see. Okay. Another question comes from Yong Kam. So the near crash detection that you mentioned on the second part, and it's a pure vision based approach, or it's a hybrid kind of approach? And the second question is, do you consider any other data source like CAN or IMU from the vehicle?
Yeah, for our part is for the near crash detection is just the vision based method. But as I mentioned, we do have the communication via the CAN network with another LiDAR-based system. But that for the project, we are doing some data collection and evaluation. So we are not use the CAN like data, like the IMU or the G-force data to detect the so the near crash. But there's potential because we have already done the communication with the LiDAR system, and we can certainly do some fusion with their system in the future. I mean.
Mm-hmm. And based on that, maybe a follow-up question. I think you mentioned the hardware setup that you guys have is kind of overkill. So I assume the computational power for that is very strong, or the computational time of your application should be minimal, right? What's the ballpark? What's the scale of the computational time for your application?
Oh, so I mentioned the overkill. That's just I mean using the Arduino Uno for the auto boot up function. I mean that's overkill.
Oh, I see.
Yeah. Because the auto boot up it doesn't require a lot of computation. So, but we use like Arduino with like maybe 10 lines of code, and you can do the auto boot up. And the overall computation, I think we on the Jetson TX2, so we just use the max. So there's different power mode on the Jetson. So we just used the max processing mode. And so with that mode, I think you can do a lot of object detection. So the latest object detection in real time. But but that's almost, I think, cost to the all the computational power. So that's why our like near crash detection, like modeling the bounding boxes, is very simple. It's just some linear regression, but that's also based on some camera model. I think that's also very efficient and works well in terms of accuracy.
Thank you. Thank you for answering. Thank you very much for your presentation. Thank you, Remy.
Yeah, thanks a lot.
Yeah. Any attendees, if you have any other questions for Remy, please feel free to add in the chat box so Remy can discuss with you. So our next presenter is going to be Dr. Yang Zheng. Yang, are you there? Can you? Oh, I see you over there. Thank you. Yeah, so you can start to share. Before that, maybe I will quickly mention this on my side. Due to some of the miscommunication between the presenter and the organizer, we left out one presentation and we are adding that at the end of this whole session. So good news, we have one more presentation at the end by Mr. Meng Zhang, and it's called Connected Autonomous Vehicle Cooperate with the Pedestrian in Industrial Sites Based on Trajectory Optimization. So we can cover that at the end of this workshop. So maybe Yang, you can start to share your screen and I can do the intro for you. So our next presenter is going to be Yang Zheng. Dr. Zheng is a postdoctoral scholar at Harvard University, working with Professor Nani and Professor Ali Malkawi. He received a bachelor and master degree in Department of Automotive Engineering from Tsinghua University in 2013 and 2015. In February 2019, he received the PhD degree in control from the University of Oxford. Dr. Zheng is broadly interested in learning, optimization, and control of network systems and their applications to autonomous vehicles and traffic systems. Dr. Zheng will be joining the Department of Electrical and Computer Engineering at UC San Diego as an assistant professor in July 2021. So yeah, Professor Zheng, please start your presentation.
Okay, thank you. Can you see my screen?
Yes, very clear.
Okay, good, great. Okay, good morning or good afternoon, good evening, depending where you are, everyone. Welcome to my presentation. My name is Yang Zheng, and I was a postdoc at Harvard, and I will join the ECE department at the UC San Diego as assistant professor next summer. I would like to first thank the organizer for organizing this workshop and for inviting me to speak today. And it's my pleasure to present some of my work in this workshop. So today I'm going to talk about some of my work on integrating autonomy into traffic systems. And especially I'm going to highlight some scalable control and optimization technique for such integration. Okay, first I would like to thank my collaborators for their support. So Professor Nani was my postdoc advisor at Harvard. Antonis was my PhD supervisor at Oxford. And Luca and Mayam are my long-term collaborator at HH. And I would like to also thank Professor Ke Qiangli and Dr. Jiawei Wang for their support about this project. They are at Tsinghua University. Okay, as we all know, autonomous vehicles has many promising effects in traffic system. Especially, they are expected to reduce traffic accident. They are expected to ease traffic congestion, and they are expected to improve energy efficiency. Also, they can bring new mobility patterns to the traffic system, such as on-demand mobility or mobility as a service. Most of these expectations are based on the unexpected or effect that most the autonomous vehicles are going to become the majority part of a traffic system. But as we all know, before that, there will be a very long stage of mixed autonomy mobility, where both autonomous vehicles and human-driven vehicles coexist. So many of you can ask many interesting questions. I think some of you will ask, how will a small scale of autonomous vehicles change the traffic dynamics? And also, how can we control or integrate a small scale of autonomous vehicles to improve the global traffic performance in addition to the performance of the individual autonomous vehicles? So these are two very interesting questions. I think most of you have thought about it or have shown some promising results from some other aspect. And in this talk, I'm going to first present some theoretical evidence of the high potential of autonomous vehicles in improving traffic performance from control perspective. And if I have time, I will also briefly touch about the practice design using distributed control and the scalable optimization for such integration. Before going to the technical results, I would like to highlight 2 benchmark experiments for further motivation. I think most of you have seen this experiment. They are quite famous. So the first experiment was carried out in 2008. So Sugiyama and his colleague put up this very beautiful experiment in a ring road setup. So there were 22 human drivers, and they were asked to drive at 30 km per hour to follow its preceding vehicle. And this environment is very simple. There's only single lane. There are no traffic lights. There are no stop signs. But we still see traffic wave emerge from this simple traffic scenario. So basically, it highlights that traffic jam can be caused purely by the stochasticity of a human driving behavior or some bad driving behavior of some human drivers. And this experiment is very, very interesting. So we know like some bad driving behavior can cause much loss of traffic efficiency. And what can we do if we have autonomous vehicle in the system? So I think most of you all have also seen this experiment. So about 10 years later, in 2018, Stern and his colleague reproduced the experiment. So they replaced one human-driven vehicle by one autonomous vehicle. So in the beginning, the autonomous vehicle was not controlled. So it's driven by a human. Then we saw the traffic wave happen again. And after the controller is activated, so the control of the autonomous vehicle can actually smooth out the traffic wave relatively quickly. And this experiment is also very interesting. It shows like in practical traffic scenario, actually control of autonomous vehicle can do much good things to improve the traffic performance. I think one speaker of this workshop is the co-leader of this project. Probably he can talk a little bit more about this later. So actually, so we have seen some good experiment results. And what I am interested in is about the theory behind it. So can we explain this kind of scenario? So can we explain why does it work? So why does the autonomous vehicle can smooth out the traffic wave? There are some explanation, and here I would like to talk about from a control perspective. And I'm also interested about does this work in other setup, like with different number of human-driven vehicles, like with 100 human-driven vehicles and one autonomous vehicle, or a few other autonomous vehicles, or in other scenarios. So does autonomous vehicle have the capacity to smooth out traffic wave quickly? Especially going to use some tools in sparse network control to abstract this traffic scenario into a network system. So where we have a one driving node correspond to the autonomous vehicle where we have direct control. And we have a bunch of other human-driven vehicles. We do not have direct control, so they are just on a controllable node. And we want to see what's the capacity of this single node that allow it to modify the dynamic of the system. Can we do this kind of a control in a large-scale system? This is the first question I would like to answer from control perspective. And another question is that if we know the autonomous vehicle have the capacity, then how can we design a good controller using limited information from its labeling vehicles? Because as we know, autonomous vehicle can only have communication with some of its labeling vehicles. And then how can we use that information to design a good controller? And how can we scale up the computation efficiency for large-scale system? And this will be the second part of my talk. If you are interested, you can take a look at the papers for control design and for efficient improvement. I will briefly touch about the topic. Okay, any questions so far? If you have a question, you can direct ask, or we can chat after the talk offline.
Yeah, I think you can go ahead. I will ask on behalf of the attendees at the end of your talk.
Okay, great. So So I'm going to talk about the first part. So basically this part about some theoretical potential of autonomy in mixed traffic. Especially I'm going to talk about stabilizability and using autonomous vehicle as a mobile actuators. And I'll introduce a new notion of leading cruise control in the first part. And if I have time, I will briefly touch about the second part, about how to design the controller, how to solve the problem efficiently using some advanced control and optimization technique. Okay, to be concrete, so let's first start with some system modeling. So just bear with me, there's a little bit more notation, but just minimum to be concrete. So in this system, we have two kinds of vehicles. The first one is an autonomous vehicle where we have direct control. The second vehicle is a human-driven vehicle. So they have a fixed car following dynamic and we cannot control them directly. So for the human-driven vehicles, they have a car following dynamic, and normally the car following dynamic is something like this. So the acceleration of this vehicle depends on its spacing and its relative velocity and its own velocity. So this will be a nonlinear function. So many works have been conducted to identify this kind of structure. They are not of human driving models to describe this kind of behavior. But here, just assume this kind of a nonlinear function to describe the car following dynamic. And at one equilibrium point, the acceleration of all the vehicle will be 0, and then the relative velocity will be 0. So basically, we have this kind of equilibrium correspondence between spacing and the velocity. And normally, so as a humans, so we often have a large spacing if we are driving at a large velocity. So basically, if we the velocity is bigger, then correspond to a bigger equilibrium spacing. It's just some fact. Okay, and then for the modeling of autonomous vehicles, so we just use a simple second order model for this kind of analysis. So basically, we can direct control the acceleration of the autonomous vehicle. So this will be a second order system. And then the global system will still be nonlinear. For analysis, we can linearize the system around some equilibrium traffic state, V star. Then we get this standard state space form in a canonical form. And for this particular structure, we know that the matrix A will have a cascading structure because it's kind of a car following dynamic. So each agent only have direct interaction with its preceding agent. So this kind of thing, structure appears in this matrix. And again, because we can only control one node, so basically only one element here is non-zero, all the rest of the element is 0, meaning we do not have a control, direct control for this kind of node. So this will be a network system with only one controllable node. And then, so this, now with this setup, so we can talk about some results from control. So the first thing is that if we remove the control, if we do not have control, all the vehicles are car following, they have a fixed car following dynamic. So basically we do not have control correspond to this setup. And it's known that in the literature that if the car following parameter satisfies some condition, then the system will be unstable. So this parameter corresponds to some sensitivity of drivers to the speed and the spacing error. So basically it's saying that if this driver have very slow response, then the system will be close to unstable. Basically meaning the eigenvalue of this matrix will have a positive real part. So this kind of some simulation correspond to different system size, this number of vehicles in the system. And for the parameter setup, we can all see there's some eigenvalue with the real part. So basically saying this system is not stable at this particular equilibrium point. And then this is the time domain simulation. So this confirms the finding here. And basically we can also see the outcome from the experiment here. So this driver has slow response to some spacing, and then it's a slow down and to catch up. So it's will drive to a large velocity, and this kind of behavior will cause some oscillation, and the oscillation will be propagating along this system, and we will see the unstable behavior as we saw in the video before. Okay, this is the first theoretical result. People know this. And the second thing is that what if we bring back the control of the autonomous vehicle? So we have one node that allows us to do some modification of the system. And then what happens if we have this kind of input here? So then in our paper last year, we proved that in theory, the system, the linear system AB is not controllable, but it's stabilizable, which means all the not controllable, which means there's a mode correspond to the ring road structure that cannot be controlled, but all the rest of mode can be controlled. So for that uncontrollable, this is stable, then this system is stabilizable, which means the autonomous vehicle actually can change the traffic dynamic fundamentally. So we can modify the system, we can stabilize the system. And this result actually is independent of the number of human-driven vehicles, which means if you have 100 human-driven vehicles, only one autonomous vehicle, in theory, it can be stabilized as well. But in practice, probably it take a longer time, it will probably take more energy. And then this result is also independent of a car falling dynamic. So no matter what kind of car falling dynamic, as long as the linearized dynamic has this structure, our result holds. And so basically, this offers a very strong control direct support for the potential of autonomy in mixed traffic. And so basically, integrated autonomy is a fundamental change of the dynamic. So we have more control freedom to modify the dynamic, to stabilize the system, and to smooth out the undesirable traffic wave. Okay, this is the second evidence. And then we can do more. We can do beyond stabilization. So basically, because the system is stabilizable, actually we can stabilize the system at another equilibrium point, not just at the original traffic state. And we have proved that the traffic velocity actually can improve to another value. So the value will satisfy some bound. So there will be upper limit, but it can be improved a lot. And this is this figure demonstrates the idea behind this theorem. So suppose we have all the vehicles are human driven, and then at the equilibrium point,
Good morning for people in America, good afternoon in Europe, good evening in Asia, as I understand the audience of Intelligent Vehicle Symposium are all around the globe. And my name is Prashant Tiwari. I'm really excited to be part of this workshop of IoT in ITS. And for my full-time work, I work for Toyota R&D in Silicon Valley. And today we're going to talk about IoT and smart connected vehicles enabling MaaS opportunities. MaaS stands for Mobility as a Service. This is a topic which is quite a passion of mine, and significant portion of my team in Toyota R&D are working on this topic. And significant, actually, this is a topic which is really gaining quite a lot of interest within automotive domain, and I'll explain to you why. So let me first set the context of connected and automated vehicles, or CAV as they go by. They're really gaining in acceptance, and they are actually coming out in masses. Toyota is a big part of a consortium called Automotive Edge Computing Consortium, or AECC, and it was formed just a couple of years ago, mainly to look at what happens when we bring these CAV or connected vehicle in masses. We did some study to benchmark and just project forward for 5 years, 2025, how many of these vehicles will be on the road. From all of our model studies, there will be at least 100 million units in the market. And if you assume that all of these 100 million units actually are going to be very advanced sensors generating a huge amount of data, some of our studies show that up to 1 to 10 exabytes of data per month will be generated by these vehicles. There is no typo. We have looked at the studies multiple angles, and that's a huge amount of data to be handled within the vehicle. However, this data also provides multiple opportunity for us to make use of it as mobility as a service, as I said, MaaS. So we'll talk about that. However, how to handle this data and how do we intelligent handling this data, how we're handling that, I'm going to talk about that very shortly. But one thing which is sure that 1 to 10 exabytes of data per month is difficult to handle or process within the vehicle. So multiple other technology needs to be evolved in order to handle that. Besides the automotive data, one more thing or a disruption which is happening across the services industry, I would say, is not just unique to the automotive sector. In last few years, both consumers as well as businesses have realized that in order to provide a value for a product, you not necessarily have to own the product. And the value is dissociated with just owning the product. So this revolution or disruption has enabled multiple business models and disrupted that also. Some of the common ones or well-known ones are in the hotel industry with Airbnb, in the smartphone industry with Apple or iOS or an App Central, and in rental car industry with Uber. Now, within the OEM or an automotive manufacturer perspective, some of this is also felt. One of the common buzzword going around is called CASE. CASE stands for Connected, Automated, Electrified, and Shared. And S stands for you can use it as shared or services oriented. So there's long-term revenue growth being generated just from this data as well as this disruption happening in the service economy. Now, how is Toyota handling this change or this disruption? As you all know, Toyota is the most reliable car manufacturer in the world. And if you've been following some of the progress within Toyota context lately, in 2018 and 2020 CES, we announced that we are also trying towards becoming the most reliable mobility service provider in the world. In particular, the announcement we made in 2018 in regards to the vehicle, which is in the bottom right, it's called ePalette. It's a fully modular, fully electrified, fully customizable, and fully shared vehicle. It's going to be the primary mode of transport for all the Olympic athletes in the upcoming Tokyo Olympics. But it's not just a concept. This is how we are also testing out multiple mobility services and the connectivity solutions, which we are currently researching on. So bringing back, what are the use cases which are getting enabled by this IoT or the big data or the connected vehicle that are coming out more precisely from the connected vehicles? Within the context of AECC, Automotive Edge Computing Consortium, we looked at multiple use cases as they are getting enabled, and some of the examples are on the screen. I would say most of these are just scratching the surface right now, but let me still name a few. Telematics, insurance, smart connectivity, mobility as a service in general, the traffic flow, remote maintenance, personalized driving experience. Lots and lots of use cases are getting enabled as we speak. So huge opportunity within the automotive context and automotive domain. Now, with opportunities are also challenges, and we have to kind of realize, and that's where the R&D importance comes into how we are solving these challenges. But let me just name a few challenges here. As we set the context that with exabytes of data coming out from these autonomous or automated vehicle sensors, we're not going to process all the data within the vehicle. So it needs to be uploaded through networks or to the servers. Now, there are challenges in terms of handling this data. There are remote servers with varying frequency and volume of data. And we have to kind of account for this heterogeneity of the servers all around the globe, not just all around a certain region, but all around the world. Second big challenge is that when we are providing mobility services to customers, they expect certain minimum guarantees in regards to reliability of the service, availability of the service, response time, latency. But even from within the context of how we handle this data internally within our servers and all, we have to have certain minimum quality of service within the processing standpoint. Now with the heterogeneity of the server, how do we kind of handle this data? That's also a big part of our research which is going on. And there are two big areas we are actually working on simultaneously to solve these challenges. The first one is called edge computing, and second is called digital twin. And I'll touch upon both of them very briefly. Now, automotive edge computing is the context I'll touch upon, but in general, what edge computing means is we are doing compute very close to the source of the data. That's what edge computing means. Within the IoT context, edge computing is one of the key enabler which is being researched all around the world, and it's really huge opportunity. I would say edge computing is probably one for automobile or OEM perspective. Edge computing is one of the biggest technology which we're looking at, primarily because automated vehicle or these connected vehicles are going to be the biggest source of data in all of IoT sectors. So that's why edge computing is one of the primary research areas for us. Let me give some example of how this data will be and what type of data will be there. So we have three types listed here. Let's say a vehicle needs an over-the-air update. So from the servers, either in their edge or a cloud server, an upload get pushed to the vehicle. So downward data exchange or data flow. If you talk about high definition map context, high definition map means that vehicles are using their simultaneous localization and mapping sensor to look at the dynamic information around them. And this dynamic information get uploaded in the dynamic layer of high definition maps. So there's an upward data exchange flow or data link to the servers. Oftentimes, when we are looking at advanced use cases, there is an application running within a server or within the car. But car is never stationary, they're moving. So as the car move, we have to also account for this application reliability, but at the same time, offloading this to one edge node to another edge node, data offloading. And this is also a big part without affecting the reliability and running the service. So those, some of these three data exchange, data flow types are the context of edge computing. At the same time, the amount of data we need to handle from automotive sensors, that's another way why edge computing is such an important area for us. Now let's talk about what is digital twin. And I'll also touch upon how this is different from edge computing. Now, digital twin primarily mean that you have a digital image sitting primarily in the cloud server, and it mimics similar to your physical entity, which is the car. In our case, within the Toyota context, when we talk about digital twin, we also actually create a twin or an image of the person driving the car and his behavior or her behavior into the cloud. And we map each vehicle and their driver behavior, primarily because some of the use cases, as I'll talk about shortly, requires us to know very precisely what each person really need, their personal driving behaviors and so on. How this is different from edge computing, let's talk about that. Edge computing by definition means that we are doing compute very close to the sensors, and these are done on a lightweight device. They can store data for certain vehicle, but not all the vehicle. And if you're talking about macro scenario, where a large fleet of vehicle or of vehicles in global environment or so, this data is humongous in nature, and that needs to sit somewhere in the central cloud. So the central data lake as well as central exo macro models needs to be on a central server somewhere, and that's where digital twin comes into picture. In another context, digital twin is different from edge computing, is that we also are running analytics model and algorithms which project and give some guidance back to the driver in terms of recommendation. And that's also requires data crunching at a large extent, and that's where the cloud servers are primary place for this digital twin. Now let's talk about, with these technology, the data being available, as well as two technology I talk about, edge computing and digital twin, what class of use cases getting enabled? One of the class we are researching heavily is called personalized intelligent driving. This really means is that we have using edge compute as well as the cloud compute or a twin in the cloud compute to really have a unique experience for the driver without having the burden of vehicle do all the compute by in a single vehicle. Let me give an example. Like when you are in a highway emerging scenario, you have a unique way of accelerating. You have a unique way, a unique comfort level. How immersed drivers, some are confident drivers also, and some are hesitant drivers. Now, can the vehicle automatically account for that? That's one of these specific use case within personalized intelligent driving. Another way of looking at is, let's say you are driving on a highway, and there are risky environment around you, which are kind of getting risky. Now, there should be a way for you to get that notification or a recommendation to do certain actions to make your environment safer and also to suit your driving habit. So these are the class of use cases we are looking with this plethora of data available, as well as using edge compute and digital twin technology. So the personalized intelligent driving use case I mentioned, we actually implemented this in with using one of our partner. And the partner is University of California, Riverside in Southern California. And the testing you're going to see, the demo you're going to see is on real life scenario with 3 real Toyota vehicles, all connected to edge and the cloud network. And let me set the stage. So there, what you'll see is when I play the video, 3 cars, 2 of them are on the highway and 1 is outside of the highway. And all 3 of them, they have no communication between the cars, but they are getting assistance or guidance through edge and the cloud network and in terms of speed advisory. And that speed advisory is unique to each driver based on their personal driving habit. And what you'll see is that all the 3 vehicles end up merging in a movie perfect scenario. We tested this out with multiple different drivers, multiple different traffic scenarios, and every time we get the same results. So let me play the movie for you of the demo. stationary vehicle at the top is a vehicle which is trying to merge.
Be careful, traffic may be merging into your lane from another roadway.
And what you're seeing on the screen is the speed advisory each driver sees. If they overshoot, it goes as red. If they're undershooting, it's green, so they have to speed up. So that was the demo we did with 3 real Toyota cars connected to Edge in the cloud network at one of our partners. So the plenty of opportunity which is kind of getting enabled with big data, with the car becoming an IoT device and multiple sensors and connected vehicle. In order to realize this opportunity, we are building what we call Toyota Mobility Service Platform, or MSPF. This really is a combination of mobility platform, our mobility platform, the data coming from the sensors, and as I mentioned earlier, the disruption within the services industry, where you're not owning the product, but still receiving value through services. And Toyota is trying to be the most reliable mobility service provider in the world, just like the most reliable car company in the world. With that, you have been great audience, and thank you. One more time, my name is Prashant Tiwari. I'm Director for the Intelligent Connected Systems Division in Toyota R&D. And with that, I'm happy to take any questions from the audience, and looking forward for more interactions if anybody wants to be in contact with me. Thank you one more time.
Going to be more convenient. On the supply side, though, we've known for a long time that automated vehicle technologies can increase capacity in the roadways. You see in 2 different videos on these slides, one from Berkeley Path, showing that vehicles that have wireless communication capabilities and can exchange information very quickly in real time can move together at high speeds very close together. Those same types of technologies have now been significantly improved for doing truck platooning technologies, where there's a huge benefit to reduce the aerodynamic drag on following vehicles. The main idea here is, though, by using information and control, we can increase the capacity of our roadways, to the extent of maybe 2 to 3 times the capacity by just filling in the empty spaces that humans need to maintain safety with additional cars that will also be safe because of the information and automation that they have. So the core idea here, if you want to increase capacity, you need to be able to move people close together and at high rates of speed. Now, I just want to remind us that moving people together at high rates of speed is not only possible via technology. If you want to double the capacity of the roadway, all it would take is everyone carpooling. If you could pick up one more person on the roadway, we'd effectively double the capacity of all of the roads in the world. If you wanted to 4x the capacity of the roadway, well, you could just pick up 2 more people. When I start thinking about 4x increases in capacity, this is capacity in terms of people moved rather than vehicles moved. This is something that is going to be very difficult to do with automated vehicles unless we change their shape and physical dimension. So we should be looking at alternate ways to increase the ability to move people beyond pure vehicle automation. Now, on the other hand, I don't believe that vehicle automation is not going to come with some benefits. Quite the opposite. I actually think that even self-driving cars at a small penetration rate can have a big impact on some of the most frustrating types of traffic congestion that we see on the roadways today. So in the time I have left, I want to show you some of the work that we've been doing to try to understand the impacts of vehicle automation to eliminate phantom traffic jams, and also some of the limits that we see with current vehicle automation systems, with an eye towards what we can do in the future if we were going to try to get high penetration rates of technologies out on the roadway that can make traffic better for everyone. So we saw this video earlier in one of the talks, the famous experiments that were done in Japan about a decade ago that carefully, experimentally isolate that human driving behavior alone is enough to create these so-called phantom traffic jams. You see the cars all driven by humans racing around the track, and just due to the nature of human driving, fundamentally the instabilities in the car following dynamics that humans operate under, you see these small perturbations grow into traffic jams that are persistent on this track. And we know that these jams don't just exist in these isolated laboratory conditions, but you can observe these on open roadways. This is a video from a freeway, from a roadway in Georgia, where again, you can see this collection of vehicles that are completely stopped, propagating against the flow of traffic, seemingly occurring without an obvious cause, but are in fact due to the way that humans drive. And that's the point, right? If you have level 1 vehicle automation systems, those replace some of the driving tasks and some of the operational domains with humans and with automation instead. And that gives us the potential to control these types of effects so that they no longer occur. I see an old friend, Bike Ho, from my days at Nokia on the call here today. You know, a decade ago, we were rethinking about how putting GPS-equipped phones in cars, even at low penetration rates, could fundamentally change the world for traffic estimation. Today, we're using those same ideas and not looking at phones as the key enabling technology, but looking at the cars instead as the enabling technology. Automated vehicles, even at low penetration rates, may have a game-changing ability to change the way that we manage traffic flow, specifically to eliminate these types of very frustrating phantom traffic jams. In 2016, we teamed up with some of our partners at Rutgers, Temple, and the University of Arizona to repeat that experiment that was done by Sugiyama and their collaborators in Japan. This time we're on a circular track in Arizona, and this car that is being traced with a black arrow is a several $100,000 automated vehicle platform run by Jonathan Sprinkle at the University of Arizona. We initially have all the cars controlled by humans, and then when the arrow turns red, it's now being controlled. One car is being controlled with a controller that is designed to smooth out the jam or to stabilize the flow on the ring is another way to look at it. By controlling that one car, the remaining 20 cars on the track, all controlled by humans, had a significant reduction in the amount of stop and go driving they experience, which led to a significant reduction in the fuel consumption. We measured the fuel consumed of all the vehicles via the OBD2 ports on those cars and measured a 40% reduction in fuel consumption when we compared the traffic in this highly oscillatory stop and go driving, which was observed when all the cars were under human control, compared to the condition where one of those vehicles is switched to an automated vehicle platform that is designed to smooth out the traffic flow. So this work was very inspiring to us to recognize that there's potential to fight phantom traffic jams with vehicle automation. But the challenge, of course, is that to scale, we can't do this with vehicle platforms that are going to cost hundreds of thousands of dollars, or we'll never be able to get to the number of vehicles needed to do this on an open roadway. So in the meantime, we've started looking at what you can do with these level 1 and level 2 vehicles that are available on the roadway today. And one of the open questions is, can the current vehicle automation technologies already get us the benefits that we saw in the previous video? Well, it turns out that quite a bit is known in terms of how these phantom traffic jams occur that date back to the traffic science community in the 50s and 60s, as well as the vehicle control communities. So there were vehicle experiments that were being done by researchers and by General Motors in the late 1950s and 60s, where they were measuring and trying to model the way that humans drive. And very quickly they realized that it's possible to see these so-called instabilities or string instabilities where small oscillations grow into large stop and go patterns. And on the vehicle control side, people started looking at what would happen if you could automate those vehicles and force them to maintain a constant spacing to the vehicle ahead, a constant distance to the vehicle ahead. And it was quickly discovered that constant spacing-based policies lead to these types of string instabilities where phantom jams arise. Later on, people in the vehicle automation space created the fundamentals of adaptive cruise control systems today, which are all based on constant time headway designs. So rather than maintaining a fixed distance to the car ahead, instead you maintain a fixed time separation, like a 2-second rule to the vehicle ahead is a way that sometimes we hear it even in driver education courses in the United States. And in terms of simulation, we've been able to simulate the benefits of potential vehicle automation designs on traffic flow. We know that these constant time headway designs can be designed such that they are string stable, meaning they have the potential to stabilize otherwise unstable human driving. On the other hand, in terms of what was available on commercial vehicle platforms, basically the first and only reference I'm aware of in prior to 2014 is this work by Steve Schlaudover and his collaborators that were augmenting a set of Infinity vehicles to build a connected automated vehicle system. And they put in the paper a reference that the commercially implemented ACC system is not string stable. So our team, and more recently quite a few other teams around the world, have been interested in characterizing the performance of current vehicle automation systems, because the traffic flow physics change when we put those systems out on the roadway. And we want to be able to characterize if they're making traffic better for humans or making it worse, even when they're operating at low penetration rates. So we went back out to the University of Arizona, where we've got a vehicle that can essentially serve as a signal generator for vehicles that are running adaptive cruise control and follow it. And we built a platoon of vehicles that all follow this lead vehicle. Okay, and the setup here is the following. The lead vehicle is going to drive at a constant velocity and then have some kind of perturbation to its speed. All of the vehicles that are following are all running a stock commercial adaptive cruise control system. And there is no communication between the vehicles, but they're all in car following mode, right? So we set the set point of these adaptive cruise control systems well above the speed profile of the lead vehicle to make sure that they're not running a cruise control mode, but in fact running an adaptive cruise control mode. And here's an example of what these types of experiments look like. So we have a straight stretch of roadway, and we'll be using this roadway to drive vehicles at approximately 50 miles per hour. The first vehicle that you'll see as it enters the roadway is a vehicle that is under complete automation, and that's for consistency of the experiments. All of the other vehicles you see on the road here are all vehicles running stock, commercially available adaptive cruise control systems. The lead vehicle slows down about 5 miles per hour, and that 5 mile an hour slowdown, as shown in the plot here, is amplified to a larger slowdown to the vehicle behind, which then, of course, has a large vehicle behind it that slows down more. The vehicle behind that slows down more until the last vehicle in the platoon is dropping below the minimum operating speed to run that adaptive cruise control system. And so we ask that driver of that vehicle to leave the experiment if the ACC system turned off. This is experimental evidence that these commercially available ACC systems are not string stable. Well, it's very difficult to test experimentally large platoons of vehicles to identify the string stability. So some of the work that we've been doing is coming up with ways that we can do this by just using either 1 or 2 vehicle experiments. So the setup is very similar. We have a lead vehicle, which is just basically serving as an input to the stock ACC system. We take the following vehicle and we model all the complexities of the real ACC system, the engine dynamics, the vehicle dynamics, as a very crude model that simply says the vehicle will accelerate or decelerate as some function of the inputs to the system, the space gap between it and the vehicle ahead, its velocity, and the velocity of the vehicle ahead. What these models can look like is something like the following. Accelerate or decelerate such that the vehicle relaxes to a constant time headway denoted by tau. That would be the 2-second rule that I referred to earlier. And there's another term here that says try to match the vehicle velocity of the vehicle ahead of you. This is just one of many simplified models that represent very complex behaviors that are happening inside this vehicle system. But the name of the game is drive the lead vehicle in such a way that the parameters K1, K2, and tau, shown in red here, can be estimated. If the parameters can be estimated accurately, and if the model that is shown here replicates the behavior of this car, then we can check the string stability of this model and infer properties of the string stability of the overall vehicle itself. And given these types of models, it's actually relatively straightforward to check the string stability. It ultimately ends up being partial derivatives of this dynamic here with respect to its inputs, its space gap, its relative velocity, and its velocity itself. Okay, so we tested through a set of driving experiments a large number of additional vehicles. I think we've tested a total of 10 vehicles at this point. Every vehicle we've tested produces waves at some frequency. In fact, another way of saying it is that none of them are able to fight phantom traffic jams in all cases. Now, that important distinction here I want to make is that does not mean that these vehicles are going to make traffic worse when you put them into the flow. It simply means they're not as good as they could potentially be in terms of fighting these jams. Remember, humans create phantom traffic jams, so if vehicle automation systems also create them, it doesn't necessarily mean that putting these vehicles on the roadway will make traffic worse or not. To do that, we need to compare how these vehicles behave relative to how human drivers behave, and that we have not yet done. Another part I want to emphasize is that in addition to confirming that the model is good, we also need to do some sensitivity study to make sure that if we have some errors in the parameters that we've estimated, it doesn't change the string instability finding. And the way that we do that is we first calibrate the model by basically minimizing some loss function that characterizes what the model says the trajectory should be and what we actually measured empirically from the data. Then we use the estimated parameters to determine the string stability. And then we set a new optimization problem, which is constrained to find the opposite stability answer. So we initially calibrate and find that the models are in string unstable. Then we recalibrate with an additional constraint that says, find me the best fit parameters that would lead to a string stable finding instead. And what we can see by adding in that extra constraint is that we would have to increase the fit of our model error by on the order of 25% in the settings when we're following the vehicles ahead very closely. So we have some confidence that those string instability findings are correct, even without doing the multi-vehicle platoon tests for all of the vehicles that we've tested. In the 11 minutes I've got left, I want to show you some of the things that we're doing now, recognizing that it's possible with very expensive vehicle platforms to eliminate phantom traffic jams, and recognizing that commercial vehicle automation systems that are available today don't quite deliver the flow smoothing benefits that we'd like to see. So what we're really trying to figure out now is how we go towards traffic flow smoothing at scale, no longer on the single track, leveraging essentially the same types of technologies that are in these ACC vehicles, but minimally modifying them such that we can deploy them in large vehicle numbers on actual open roadways in the United States. So we've got a project which is known as Circles, which is really aimed at exactly this, traffic flow smoothing at scale, getting beyond the one vehicle to potentially 100 automated vehicles that are in a real roadway trying to smooth traffic flow overall. Of course, to do this, we also need to scale the team. We've got now more than 45 researchers that are representing 5 different universities, 2 vehicle manufacturers, including Toyota, and the Tennessee Department of Transportation, who are all helping us try to figure out how to build test beds and vehicle technologies that can achieve this goal of making traffic flow better for everyone, even though only a subset of the vehicles have the technologies deployed on them. On the vehicle automation side, it's definitely possible to do a lot today with these vehicle platforms because they have so many capabilities running right off of the showroom floor. So our lab has purchased a stock Toyota RAV4 from which we can read the CAN bus data that gives us the critical information about the surrounding environment for the vehicle. So from a control perspective, we're able to get information about the distance to the vehicle ahead, shown from this dash cam video and visualized on the plot above. We know how fast the vehicle in front of us is moving. Again, these are critical bits of information you will need in order to control this following vehicle to maintain safety and at the same time try to smooth out the traffic flow overall. On the instrumentation side, it's very easy to instrument a circular track with a camera and capture the dynamics of all the vehicles. It's much harder to do this on an open roadway. In fact, vehicle-based trajectory extraction on roadways has been an area where there's been very limited data until recently for the traffic science community. In 2006, the US DOT sponsored the Next Generation Simulation Project that produced several data sets, one of which is the Interstate 80 data set that captured about 1,600 feet of vehicle trajectories that were collected over a series of about 45 minutes. Now, this data has served as the backbone of the traffic simulation community, but of course the challenges are that was data from 15 years ago, or 10 years ago, and we need it to be longer in length, longer in time, and we'd ultimately like the ability to be able to put our own vehicles in this trajectory stream and understand the consequences of putting our control algorithms out there on the overall flow. So with that basic idea, we've been working very closely with the Tennessee Department of Transportation that is currently in the process of building about a tens of millions of dollars project called the I-24 Smart Corridor. I-24 has about 150 to 170,000 vehicles a day that pass through it. And it has this characteristic phantom traffic jam behavior that we know is very fuel inefficient and we'd like to try to eliminate. What we're doing is taking a subset of this roadway, about 6 miles of it, and instrumenting it with several hundred 4K resolution cameras that all provide overlapping fields of view that allow trajectories to be extracted, much in the same way that the NGSIM experiment did many years ago. In August of 2020, we recently finished construction on a demonstration phase of this project where we have worked with partners to elevate 3 poles, each 110 feet tall, that carry 6 4K resolution cameras at the top of each of these poles. This allows us to capture about the same length of the NGSIM experiment, but from dedicated infrastructure that we will now be able to use continuously throughout the day to collect vehicle trajectories from all the vehicles that are running through here. Just to give you an idea of how fast this construction is occurring, this all took place on a Sunday morning in about a 5-hour period. The actual poles were elevated in something like 11 minutes, 14 minutes, and 8 minutes respectively. So these poles are going up very quickly. They're all tied in together on a fiber network, and that's allowing us to get this 4K resolution video data from which we can extract trajectories. So the construction completed at the end of August. We've since then built in all the camera holding devices and elevated those, run unit tests on all the poles, and have actually started doing tests to confirm that the high fidelity video feed is all arriving at a hub building where we are storing that video data. So we're currently completing some burn-in testing of the system, but those numbers look good so far. We're seeing something like 99.95% of all the frames captured from this video data being stored by our systems that will ultimately allow us to do trajectory extraction. On the trajectory extraction side, it is a non-trivial feat to produce trajectories out of 4K resolution video data in real time, although the overarching process to do it is a relatively standard approach. We start with an input scene from a video and use a detector, pick your favorite YOLO or ResNet or other detector, and locate the bounding boxes of the vehicles that are in the scene. Then we track these vehicles over many sequences of frames by running a Kalman filter that describes the dynamics of these vehicles in the scene and where we should expect to see them in the future, so that when we get another update, we know which vehicles are which and we can produce the trajectories across the scenes. The final step, of course, is to take the bounding boxes from the image space and convert them into the real world space. Just to give you an idea, this is a 5-minute snippet of video from one camera that we were doing a unit test on, and you can see already just the type of scenes that we'll be able to collect with this system. We carefully designed these camera views to not only be overlapping, but also to make sure that they are not providing occlusions. In other words, we're not going to have the case where vehicles are hidden behind other large vehicles based on the vantage points that these cameras were installed in. I want to just give some thoughts in terms of the scale of data that's already being collected from this validation system. I mentioned the NGSIM experiment. One way to kind of understand how much data was produced in that data set is to count up the total number of vehicle miles traveled in the trajectory data. So there was 45 minutes of data, quite a few cars that passed through. You sum up all the distance traveled by all the cars and you get about 1,800 vehicle miles traveled in that data set. In 2018, there was a new data set that's also been quite important for the traffic science community, known as the HID data set, collected by drones on a freeway in Germany. That data set was 24 hours long and produced about 25,000 vehicle miles traveled of trajectory data. The I-24 system that I just showed you with the 3 poles and 18 cameras, in a year of operation will produce on the order of 16 million vehicle miles traveled. This is really important because this is going to give us the ability to completely characterize the way that humans drive. And importantly, as we put our own vehicles into the flow, we'll be able to characterize the interactions, both local and non-local, that our automated vehicles have to the overall traffic flow. One way to think about it is that if you have a vehicle which is safe locally but causes lots of aggressive lane changing in its wake, we want to be able to capture that because that's not a desirable feature, and it's hard to do that using only sensors that are on board the vehicle. Obvious disclaimer that the NG sim experiments and the HIDE data sets are available today. Those are real. The numbers that I'm quoting here are based on what we expect to collect over the next calendar year. So stay tuned for more information about when that data becomes available. So in summary, I just want to wrap up and kind of highlight where we're headed, right? So we built a test bed now that consists of a relatively short stretch of roadway, 1,500 feet, but we'll have the ability to track 150,000 plus vehicles a day to start building really high fidelity simulation environments to test our traffic flow smoothing capabilities. In the meantime, we're also expanding the test bed, going from this 1,600 foot stretch to a multi-mile corridor. And in the process of developing the simulation environments and the vehicle technologies, we're aiming to run large-scale wave smoothing experiments in the not too distant future, where we'll be working with fleets of on the order of 100 vehicles to try to smooth out these phantom traffic jams. I want to thank you for your time and attention, and also acknowledge the great team of students that I have that have really enabled us to tackle some pretty challenging problems, both in theory and in practice. With that, thank you for your time, and I'd be happy to take any questions that we have time for.
Thank you very much again, Professor Work, for a very interesting presentation. Before diving into details, maybe one detailed question. I have a general question regarding the Circus project that you mentioned. Is there any requirement for maybe CAV or intelligent vehicle penetration rate for that project, or it's general? All you assume that all vehicles are connected vehicles or approved vehicles?
That's a great question. So just to set that up a little bit more carefully, the penetration rate of the vehicles that run a set of traffic jam smoothing technologies is very important. On the ring, we showed that about 5% is sufficient to stabilize the flow. Now in the real world, not on a ring, you have multiple lanes of vehicles, and you have vehicle drivers that may not be paying attention. You have grade, you have all kinds of other visual artifacts because there might be a bridge overhead or a turn in the roadway that can all basically either help or hurt your ability to smooth the traffic. And so we're kind of very interested in understanding the differences between what is required in the low penetration rate setting. Can we do it with 5% penetration rate on non-trivial geometries, non-round circular tracks? I think the following statement is true, still leaving me quite a bit of gray room to wiggle around. I'm confident that deploying any vehicles that are string stable in the flow is going to help benefit the vehicles that are immediately following them. Whether or not they can completely eliminate traffic phantom jams altogether is clearly not, it's not possible with only a single vehicle, right? As soon as the vehicle behind you does something bad, those jams are going to show up again. But I think the interesting question is just that. Do you need 5% on the open roadway or 10% on the open roadway? And how much benefit can you actually get from vehicles that are working together to try to make traffic overall? Our hope is that it's small, that's in that type of neighborhood.
And maybe following this same question, just in case we have, say, 5% of our equipped vehicles, do you consider any perturbations from the driver behavior vehicles or the legacy vehicles? Because different drivers, they might have different, behaviors in terms of following the ACC vehicles or equipped vehicles. So do you consider any of those driving error or like driving perturbations?
Yeah, so that's a great question. I mean, let me try to make it even more complex, right? The real issue is that it's very easy in simulation to test controllers in the environment where all the other human-driven vehicles follow an ordinary differential equation. I can't name a person that follows an ordinary differential equation when they drive. Real drivers are far more complex. And so the issue, and part of the reason we're putting up all this sensing infrastructure, is to get better models of how real humans drive, so that in simulation, which is a whole lot cheaper than real world experiments, we can start to really break the controllers that don't work and produce controllers that are robust to the variations of real human driving. But yeah, the other complexity is just the following, right? I believe that semi-truck drivers are far more likely to be string stable drivers than passenger vehicles because they can see further and they're very sensitive to their fuel prices. And so you might have drivers that are helping the cause today and drivers that are making the cause worse. What our hope is that by taking out some of the human variability and instead using some of the vehicle automation, we can get rid of some of the worst driving features of humans and push more towards a beneficiary environment for all.
Sounds interesting. Thank you. So maybe two detailed questions. One from Kanak is that how much did it cost to install the 3 poles and instrument in the video cameras?
That's a good question. I don't have the number right off the top of my head. Just to get some round numbers, the cameras themselves are on the order of about $3,000. They have to have all kinds of extra capabilities in terms of their weather tight features and so on. So you can already do some crude math in terms of, call it $4,000 times 18 cameras. The poles themselves are also not cheap. How expensive they are off the top of my head, I don't remember, but they're in the order of tens of thousands of dollars. So not expensive in the context of paving lanes, but definitely not cheap in the context of, you know, certainly more expensive than the cameras are. But this is exactly kind of the thing that I think has actually hindered the traffic science community for so long, because it's so expensive to collect this type of data. You need this kind of dedicated infrastructure. You know, drones are great for getting a small subset of data, but if you want to be able to monitor the same roadway 24 hours a day, you need to actually pay for physical, real stuff, concrete, steel, fiber, and cameras to be able to do this continuously.
Got it. And I think there are 3 more questions in the chat box. So maybe Professor Work, you can answer them by typing into the chat box due to the time limit. So we may go to the next presentation. Thank you very much again for. So I'll introduce our next presenter. Maybe Kanak, you can start to share your screen. Next presenter is going to be Kanak Burben-Thompson. Dr. Burben-Thompson is a research engineer in the College of Engineering, Center for Environmental Research and Technology at University of California, Riverside, where he leads the Sustainable Freight Transportation Research Program. He has over 20 years of research and development experience in the areas of sustainable transportation, vehicle energy and emissions modeling, vehicle routing and navigation, connected automated vehicles, intelligent transportation systems, traffic operations, and traffic simulation. Dr. Burben-Thompson currently serves as a vice chair of the Measurement and Modeling Subcommittee under the Air Quality and Greenhouse Gas Mitigation Committee of TRB. He is also a member of ITE, IEEE, ITSCA, and SAE. So, Kanak, you can go ahead.
Thank you, Ziran, for the introduction, and hello, everyone. It may be good morning for some and good afternoon for others. Thank you the organizer for inviting me to be part of this workshop. Very pleased to share our work on the field implementation of heavy-duty vehicle application that help improve energy efficiencies. I would like to start off by acknowledging all the contributors of this work. It takes a village to make it a successful, involving public agencies and private sector, in addition to university researchers. Another acknowledgement for the agencies and organizations that support the work. All right, so I would like to kind of start by providing some context and motivation for this work. Some of you may be familiar with the freight movement in Southern California, and you may know that the ports of Los Angeles and Long Beach together carry about a third of total U.S. container volumes in the U.S. So yeah, think about it like a third of all freights kind of go through these 2 ports. And that's why they need a lot of trucks to move containers in and out of the port to the local warehouses before being distributed throughout the country. Now there are more than 15,000 heavy-duty trucks that are doing this job around the ports. Now, these trucks are not the same as those that drive on freeway across state, right? They don't just cruise on freeway for a long time. Actually, they drive mostly in urban areas close to the ports. And when these trucks drive in urban areas, they will have to encounter traffic signals and intersections. And yeah, at that location, there's a lot of inefficiencies, right? When trucks have to come to a full stop at red light, it increases their travel time, increase their fuel consumption, and produce a lot of emissions as well. So one thing that can be helpful in terms of reducing those inefficiencies is connected vehicle application. And the one that we are using right now is called connected eco-driving. And the concept is maybe familiar to many of you. Basically, if you are able to communicate with traffic signal, receiving signal phase and timing information from the signal, then you are able to use that information along with the current state of the vehicle to decide an approach that will optimize your either travel time or your consumption and others. Now, once you are equipped with that information and you are driving toward a signalized intersection, there are 4 possible scenarios, as you can see on the slide. The first one, if you are lucky, you are getting green light, you can just cruise through, no need to change anything. The second scenario is that if you are getting green light, but it's about to turn red, so you may want to speed up a little bit in order to pass through the intersection on green. The third scenario is that you are getting a red light, but you know that it's gonna turn green soon, so you may want to slow down ahead of time so that you reach the stop bar or the intersection by the time the light just turned green, and that way you avoid having to come to a full stop. But in some cases, that may not be avoidable, and you still have to come to a full stop, which is scenario 4. In terms of system architecture, so we have to have 2 sides of the coin. We have the infrastructure side, and then we have the connected vehicle side. In terms of infrastructure, there are many ways of instrumenting or enabling connected intersections. So in the diagrams, there are 2 architectures that you can see. The first one is all the intersections, if they are already connected to the city TMC, either to fiber optic or whatnot, then it may be easier to just connect to the city TMC and get SPAT data from there. But if that's not the case, then you can also instrument the individual intersections and then have those intersections send SPAT information to the server directly. On the vehicle side, we have 4 different major modules. The first one is localization, which is to be aware of the current location of the vehicle with respect to the intersection. So basically, this is just done by GPS or GNSS, and then if you have the map of the network, then you can do a map matching to determine the distance from the intersection and also the travel direction. And then the next module is perception. So aside from the vehicle, the connected vehicle, you have to be able to be aware of your surrounding, right? So this is the usual sensor, whether it be camera or radar, to send the vehicle in front of you, and then use that information in the design of your trajectories, which is the next module. Once you have the information about the location of the vehicle and use that information to get SPAT data from traffic signal, and you are aware of what may be blocking the path of the vehicle, then you can use all those information to optimize the vehicle trajectory in a way that minimize fuel consumption or travel time. And the last part will be the control module, which is you provide that optimized trajectory implemented automatically or provided to the driver and have driver try to follow that as best as he could. So we have worked with local agencies in Southern California to instrument connected signalized corridor close to the ports of Los Angeles and Long Beach. We have 3 separate corridors, and on each corridor we have 5 connected intersections. You may see on the right here that on a single corridor, it's not that every intersections are connected. With limited budget, we can only connect 5 intersections for each corridor. In terms of making them become connected intersection, basically we install a router that connected to the existing traffic controller. And then the router basically just forward spat information from the traffic controller to our server. And this was done back in 2018. So we were still using 4G LTE at that time. On the vehicle side, the instrumentation include basic devices and electronics as you would find in any automated vehicles. So we have onboard computer, we have radar sensor, might be a little hard to see here, but it's right above the license plate here. And then GPS, router modem, and then the user interface, which is placed very close to the driver's side so that he can easily see it. So a little bit about the driver vehicle interface. We opt for a very simple design to make sure that it's not overwhelming the driver. So if the driver is approaching the intersection when the signal is green, what he will see is he will see that from the signal head, the current status of the light is green, and then he will also be given a speed band which show the range of speed that if he stay inside this band, he will get to the intersection when the light is still green. And then there is also a symbol that show the speed limit on the current road, and this speed band is capped by the speed limit. So we will never recommend the driver to drive at speed over the speed limit. Now, if the driver is approaching the intersection while the signal is red, again, it will be the same thing where he will see that the current status of the traffic light is red, and then he will still be given the recommended speed band. You may be surprised that why there is a recommended speed when the light is red, and that's because the system know when the light gonna turn green and can calculate what range of speed will allow the vehicle to arrive at the intersection when the light turns red. Now, in cases when it's not possible to avoid stopping at the red light, then once the vehicle becomes fully stopped, then the system will show the timing countdown, so the driver can know how many seconds are left before the light turns green again. And whenever the driver is following another vehicle, then he will be notified that there is preceding vehicle ahead, and that will turn off the recommended speed because when there's preceding vehicle ahead, we want the driver to focus on the vehicle ahead and make sure that he doesn't cause any accident. So last year, we conduct few trials of the system on real road, which is in Carson, California, close to the ports. And we also organized a demonstration in March, attended by almost 100 attendees. And yeah, we just took the attendees on the truck and then drive around the route that we decide. It was a successful event, and yeah, I will show some videos from the field trials. This is the acceleration scenario. Right now, the light is green, and you see that the system tries to encourage the driver to keep up the speed because it knows that the light is going to be red soon. And notice that the upper bound of the recommended speed is not at 45 precisely, and that's because it's capped by the speed of the preceding vehicle. In the deceleration scenario, right now the light is green, and you don't see any recommended speed because there's no feasible speed that will allow the driver to get this green without exceeding the speed limit. Now the light turned red, and there is recommended speed because the system knows how long the red phase will be. So it encourages the driver to slow down. And now when the light turns green, then yeah, it encourages the driver to speed up again. Based on those initial field trials, we try to extract trajectories under different scenarios and try to match trajectories when the drivers had used the system versus when he did not. And based on the best match that we can find, we estimate the fuel savings due to the system, and we found that for the acceleration scenario, the fuel saving was around 9%. For the deceleration scenario, the fuel saving was around 4%. Now, these numbers are not as robust because the traffic condition that the driver faced and all the other influencing factors that happen when the driver drove these trajectories may not be comparable, right? Because in the real world, there are so many factors that can influence the effectiveness of the connected eco-driving system. So yeah, I list some of the factors here: traffic patterns and surrounding vehicles, and even weather. So in order to do a more robust evaluation of the effectiveness of the system, we opt for a simulation-based approach. And in simulation, you can control all those factors, right? So it's like doing a control experiment. So we did that for 4 corridors, and for each corridor, we run the simulation 100 times. In the simulation, so basically we use VSIM, traffic micro simulation software, and implement the algorithm that calculate the optimal speed for the truck using spat signal and other information online. And by online, means the calculation was done during the simulation run. So first of all, the online algorithm, which is implemented as a drive model DRL2, signal and Q data from VSIM, and then it estimates the current and target state that the vehicle is in. And using the random forest model, it determines the optimal or desired acceleration, and then request that acceleration to VSIM. VSIM has safety logic that may deny the requested acceleration. And if it's denied, then it's kind of loop back again. But once it's approved, then VSIM will implement that desired acceleration request, and then everything loop go to the next time step. On this slide, you see you see the impact of the algorithm on the vehicle trajectories. So this is just one example intersection on the left-hand side without the connected vehicle driving system. These are 100 truck trajectories from the 100 runs, and you will see that all of them will have to come to a stop at that intersection. So which is quite striking. But with the connected vehicle driving system, for many runs, the system was able to advise the truck to avoid coming to a full stop and be able to pass through the intersection at a higher speed. For the trajectories that you saw, we calculate the energy and travel time throughout the corridor. So we have 4 corridors on 2 roads and in both directions. And when we look at the median value of all the 100 simulation runs, we found that the travel time impact is negligible, right, between less than 1%, but the energy saving is substantial. It varies by the corridor from 7% to 17%. So just to wrap it up, so we were successful at doing the field trial and demonstration of the connected vehicle driving system for heavy-duty trucks. And that's thanks to the strong partnership between all the stakeholders from both public and private sectors. Early evaluation results of the system are promising. From the field results, the initial field result, we see a field saving of 4% to 9%. But with the extensive simulation evaluation, we see that potential energy saving are 7% to 17%. You may ask why it's so different. And one of the things is that in the field, it's human driver. But in the simulation, it's the optimal trajectory. So whatever optimal trajectory that our algorithm decide, we can implement it, which means the simulated truck was able to follow that trajectory precisely. But in the real world, the human driver was not able to do that, and that's why the benefit in the real world would be lower than what you would get from simulation. And yeah, based on what we have found so far, more work is still needed. So we want to see the benefit in real world under a variety of scenarios. So more real world driving data collection is needed. And yeah, as we can see that with human driver, it's very hard to follow the optimal trajectory precisely. So one option could be to automate that longitudinal control, have the truck follow the optimal trajectory automatically. Another thing is that right now, the algorithm optimized for the truck, the connected vehicle, without considering the impact on surrounding traffic. And that kind of is an optimal solution at the vehicle level. It may not be an optimal solution for the system level because the trajectory of the truck may impact trajectory of surrounding vehicles in a negative way. So yeah, we are looking to introduce cooperative behavior in the future so that we can optimize for system level benefits. Thank you again, and if there are any questions, I'd be happy to answer them either live or via chat box.
Thank you very much, Kanak. If any questions are coming from attendees, please feel free to add it in the chat box. I actually have 2 general questions. The first question is, pretty much all the slides that you showed or research that have been done is based on the Volvo truck, right? The heavy duty truck. Do you see any difference for this technology to be applied to a heavy duty truck, to a light duty sedan, or it's pretty much the same thing?
Yeah, the algorithm is applicable broadly to any type of vehicle. The only thing that needs to be calibrated is the solution table. For different type of vehicle, they have different powertrain characteristics. But once you are able to calibrate that, then everything else is the same.
I see. I see. So it's a general algorithm for all vehicle types, right?
Yes.
Mm-hmm. And the following up question is, you showed that there was a demo to the general, more like public agencies or some other entity stakeholders. How do they receive this kind of new technology? Do they think this will be great for their cities, for their agencies in the future, or they think this is just good to have but not necessary?
Yeah, I think there are a lot of interest from the public agencies, but they're still unsure of the effectiveness because on the demo day, we were not able to answer that question. We generate a lot of excitement about the technology itself, but at that time, we don't have the evaluation results, so we were not able to tell them that if they implement this technology, what are potential benefits to the driving public. So yeah, later on, after the end of the project, we hope to organize another workshop so that we can show them the evaluation results. And hopefully that will spur more interest for them to move toward more implementation.
Got it. Got it. Thank you. Thank you, Kanak. So due to time limit, we might move to the next. So for all the attendees who have any question, please feel free to ask lively in the chat box, as well as contact Kanak through email as well. Thank you, Kanak.
Thank you, Ken.
So our next presenter is going to be Jibo Sanyao. Jibo, can you start to share your screen, maybe? Thank you. So Dr. Sanyao directs the Computational Urban Science Group at the Oak Ridge National Lab. He brings a unique blend of computer science with applications in geosciences, technical, institutional, and strategic leadership with a track record of technology development, commercialization, and national recognition. His work falls at the intersection of high-performance computing leaning towards the exascale, extreme scale data and analytics, simulation and modeling, visualization, scalable machine learning, and sensors and controls, building both research and operational systems. Dr. Sanyao holds a PhD in computer science from Mississippi State Universities, and he is a member of ACM, AGU, IBPSA, and a senior member of IEEE. In 2017, he was named one of Knoxville's 40 under 40. So please go ahead, Sanyao.
Thank you, Ziran. Can you hear me all right?
Yes, clear.
Perfect. Thank you for that nice introduction. So yes, my name is Jibo Sanyal, and I lead the Computational Urban Sciences Group at Oak Ridge National Labs. I have one slide about what we do. Often I get asked the question, what kind of urban sciences do you do? So this slide that you see here, this came out of one of our projects that we did where we were trying to look at the complex interactions of things like transportation, urban atmosphere, the buildings, and then all of this being driven by socioeconomic activities. And we tried to look at how can we use some of our high performance computing equipment that we have here to help understand some driving questions. Our angle has always been to look at these complex interactions between these systems, because by themselves, particularly this audience has a lot of knowledge about the transportation sector. It's a very mature field. Similarly, the urban atmosphere is also a very mature field. But how much do each of these domains talk with each other? We're going into an era where there's going to be more and more data, exabytes of data from just a single car, is what I heard earlier today. And all of these interact with each other. So we look at all these complex interactions. And this slide here is merely a representation. It's not the complete picture. The complete picture is very complex. But notionally, this illustrates the kind of landscape that we tend to work in. With that, today's talk is about what we are doing for Chattanooga. So we've been engaged with the city of Chattanooga in Tennessee to build a digital twin of their transportation ecosystem. This is a joint project. This is a joint project between Oak Ridge National Labs and the National Renewable Energy Lab and several partners in the state and in the city. There's at least one other individual from the project team that's on the call today. I want to call out Kichao Wang. He's been working from NREL and he's a key member of the team here. So what are we trying to do? So there's three main components in this digital twin that we are building for the city. We have built actually for the city. We're 2 years into the project and we've just been renewed for another 2. The three main components that comprises this digital twin is first, situational awareness from bringing in many real-time data feeds from a variety of proprietary systems. So what that gives us is essentially observability of what's happening now. Of course, once that data comes in, we want to be able to understand what can we accomplish or anticipate using the simulation and modeling capabilities, the machine learning technologies that are available to help identify and evaluate improvements. Be able to anticipate where there might be congestion, for example, and so on. The third component in our digital twin is to actually take the modeling component, which is fed by real-time data, and then use that to control something in the physical environment. So this is that piece where we actually algorithmically change certain things to then change that future outcome that we had evaluated, recompute it back again, and get into this loop of being able to control something with near real-time data. And our goal has been to accomplish a 20% energy savings for the whole region. Our cyber-physical control has been only in a small area of the city along one corridor. However, the rest of the work, our situational awareness work, our modeling and simulation is for the entire region. And there's a reason for that. You just don't jump in and start controlling all 300 plus signals in a city. That's a little risky. So we've started with one corridor, but we do have the next phase, which I'll speak about briefly, to do this at a larger scale. I will also say that initially we thought 20% was rather aggressive, but we ran some experiments and we found some very encouraging results that I'll talk about later. And I now feel like not just 20%, with a combination of all the different things I heard today, implementations of those, and in the real world, I do believe we have an opportunity here to significantly make a dent in that energy budget for a city. So in all of this, of course, data is key. And we've been really fortunate to work with partners like the Tennessee Department of Transportation, the Chattanooga Department of Transportation, along with their Metropolitan Planning Organization, the Georgia Department of Transportation, because if you look at the first graphic on the right here, Chattanooga is really split between Tennessee and Georgia. We've also worked to different extents with TomTom data and data from ETRI. A quick summary here, I won't get into this, but essentially at this point, we have somewhere around 500 or so data streams that are coming in. There are 7 proprietary vendor systems that are across these multiple institutions that are bringing in all this real-time data. We also have some 40-something additional data layers, some of which are very dynamic, some of which are not so dynamic. And all of that have come in and we've built a tool and a platform, which I'll show you in just a bit. I do want to say briefly that the radar detector sensors from TDOT, bottom right, there's about 280 of them. It gives you an illustration of the density of these sensors. There's roughly every half a mile, there's one sensor, and the closer and inside the city you get, it's less than half a mile. And every 30 seconds or so, between 20 to 30 seconds, we have data coming in for every lane of traffic. So lane occupancy, speed, and classification. Although the classification wasn't calibrated very well. So having spent 2 years, there are a few things that we have accomplished so far. So we have stood up a tool that provides this situational awareness capability, and our collaborators have been given logins. We spend quite a bit of time on identifying metrics, because unless you are able to measure something well, how can you tell you made a difference? Our metrics are in four broad categories, three really main categories. There's energy, because Department of Energy is really interested in understanding energy impacts, and of course mobility, and then safety. There's also a metric that NREL has built recently and has been awarded numerous accolades. It's called the measure of energy and productivity. The logic being, if you just don't drive anywhere, your energy goes to zero, but your productivity also tanks. So it's a weighted, and weighted is not the right way to express it. There's a lot of math behind it. It's a measure of energy and the productivity that provides a measure of what that looks like for different types of strategies. We also have industry accepted MAP21 metrics that we have incorporated, as well as for individualized signals, we have the automated signal performance metrics that have been implemented. On the modeling and simulation side, there's this aspect of looking at things at scale. So that's the mesoscopic simulation of the whole region. And then also looking at individual corridors and what that looks like at the macroscopic scale. So we've been doing quite a bit of that to help inform what kind of strategies could be useful. Now, on the data science side, we have done quite a bit of work on representing all the movement that you can see in a way that it's intuitive and useful for a traffic engineer or a planner. We have done quite some work on RDS, which we will show shortly, and we've been looking at signal performance as well. And then I'll talk about the cyber physical control as well. So here's a video that I had recorded, I think way back in January or something. So this is an old video. I decided to just go ahead and use it. The tool looks a little bit different than this right now, but what you're looking at is for every 15 minutes, an aggregate of what the speed profile looks like, speed and volume profile looks like for the whole region. And we can go back onto any day in the last year. Now it's more than a year, almost a year and a half, and start looking at this data. So there's a high-level overview. There's all these incidents from 911 and other sources that are coming in. We also have Waze integrated into it. And then there's also a forecast of what the weather is going to look like by zip code for the region. We also have a region view, where on the left-hand side, you have a large number of all these 40-something layers that I've been talking about. All of that is listed, and you can begin to enable them and start fusing this data in one platform. You know, you can have a GIS tool that brings in all the step-up data, but bringing in proprietary data, live real-time from 7 different systems has been something that we're pretty proud of. Now, each of these dots that you see, the green dots, these are individual radar detector sensors, and you can query each and every one of them. Now, TDOT is amazing. We asked for data for the Chattanooga area. We do have data from Nashville, Knoxville, as well as Memphis for the radar sensors. We also have all these intersection level cameras from GridSmart. I believe they're close to 100 now in the city. They're actively installing more. We also found interesting things, like you see that node data on the right there. That's because every time one of these cameras are reset because maybe it moved a little bit and somebody hits a reset button, what happens is the zones that are assigned begin to get new GUIDs, so new IDs, and that breaks the history of what that data used to look like. So since we discovered that, we've architected it in a way that the provenance of the data is maintained. But like I said, I captured this video back in January. So as you can see, you can query this data, look at all kinds of things like the SmartWay cameras that Dan has been using for a lot of his work. You can bring all kinds of other related data such as Waze and so forth. Let me see if I can forward this just a little bit. With Waze running, my mouse becomes really slow. Well, let it play out then. It's probably 5 minutes more. So this goes into illustrating that we can bring in infrastructure data like the local roads, the ramps, the fire stations, law enforcement, schools, things like those. It's interesting because often when there are incidents that are happening, it's important to understand where that is happening and under which jurisdiction they fall. What's also pretty common in the traffic world is to look at things along corridors. So we have a way to define a corridor like that blue box that you see, and then it will pull up whatever sensors are available in that bounding box region. You can slice and dice and start looking at this data. So it'll pull in the radar detectors, the grid smart cameras, other feeds as well. Now, we also have an area where you can look at incidents, and these are classed by physical year. Again, at the time of this recording, that live integration of these feeds wasn't completed yet, but now we have all of those feeds and all of these different categories of incidents and being able to slice and dice them now available online. This is what it looks like for the whole year, heat maps of incidents by time of day, which can then help inform which areas one might need to start looking into. There's also metrics, and I'll talk about that briefly a little later. We built it in a way that someone can go in and start using a quick start guide. For example, what you're seeing here, there's extensive help to jump into the tool and start using it. All right, so moving on. Here's just a screenshot. I always keep a screenshot in case the video doesn't work. But in terms of metrics, we've looked at, like I said, the mobility metrics. So there's macroscopic and microscopic metrics there. We've looked at safety. These include things like looking at injuries per capita and also at intersection levels. And then, of course, the energy usage. When it comes to looking at a specific corridor for starting to investigate what we could do with employing control strategies, we started with a place called the Shallowford Road area. And for those of you who know the Chattanooga area will know that there's a big mall there and it sees some pretty bad traffic. What the graphic on the right-hand side, the table on the right-hand side illustrates are when we want to control something, given the horizon of our control, so if it's every 5 to 15 minute interval, or if it is hourly, what are some of the kinds of things that we can do in this area? Of course, to this audience, I saw a lot of the literature and history of the traffic control here, so I'm pretty sure this requires no introduction here. We have been looking at that stretch there to see what is doable, particularly on the cyber physical side. Now, we also have had lots of data. And so Stan Young and a few others from our partner lab, they started looking at, can we use probe data to understand how these signals are performing? So to tell you what we're looking at, this is along the Shallowford Road corridor. And on the left-hand side are all the intersections along the road. There are 3 metrics here that were computed. So delay at those intersections, percentage of stops, and level of travel time reliability. And then the numbers that you see are basically hour of the day. What I want to point out is if you look at the stop percentage, right in the middle, there's a massive percentage of stops in the middle of the day. Now, usually the simulation VisSim or Synchro that is used, they're often done for the morning peak and the afternoon peak. Well, in this case, the data indicated that the midday was the worst time of the day. We're now looking to expand this work to a larger region, but we use this to then start looking at what kind of changes we could make. Here's another example of what we have done in terms of computing the automated traffic signal performance measures. The graphic that you see on the top left, it's called a chord diagram. I often call it the soccer ball diagram, but essentially what it does is it weighs these different segments of that circle by the volume that we see going from these 4 cardinal directions. This was presented by Ann Berries, who developed it and presented it at National Academies workshop, and it was exceptionally well received, that in the sense that it really illustrates really well how a given signal is performing given volumes going across different directions. There was an extension of this work as well, where we could have all these plots to look at arrivals on red and how those are changing as we make changes to the signaling infrastructure. The 30-second radar detector data that I talked about earlier, one of the guys on the team, Howen, he spent some time looking at, can we take that data and emulate what flow actually looked like for the whole region with that high density of data. So there's a macroscopic view where you can get a sense of what traffic is beginning to look like at a larger scale. But then the graphics on the right-hand side is when you start zooming in, you can look at a mesoscopic view. And then at microscopic view, because we have data for each lane of traffic, he's come up with a way to look at how individual lanes are performing. So you could pick a certain time of the day and then identify how well a particular lane design has worked. So right now we are awaiting review on this. It's been submitted to a venue. And then there's this picoscopic view where as these vehicles exit, we're merging data from the radar detectors with grid smart data. So Tennessee Department of Transportation data with the city's data. And as these exit from the interstate, they start showing up on the grid smart cameras. This is quite interesting work. And then we've been also looking at freight, particularly trucks, and how trucks are moving in the area. I want to distinguish between trucks and freight here. And understanding how trucks move through this area is quite important, because by different estimates, it's either the 4th busiest freight corridor or the 17th most busiest freight corridor. Either way, it's a busy corridor. And we have found that getting data from ATRI or some of these other probe sources, those data are quite expensive. So while we have some of that data, we have started looking at something similar to what Dan has been doing, which is to look at image analysis from the SmartWay cameras. There's about 110 or 120 of these cameras in the region. And we have been using basic algorithms, YOLO algorithms, to identify the cars and the trucks, fairly straightforward. And then we were able to correlate this with the radar detector accounts. And as we expected, they work reasonably well. This works reasonably well, except when it's at night, the quality is poor, or if the weather is really bad. We are now looking to extend this proof of concept to the larger region, be able to create these ubiquitous flows of freight in the whole region. Pretty excited about the next phase of this. On the simulation side, we have looked at different approaches. Kichao had been looking at the model predictive control approach. A few other approaches have also been looked at. And what this really illustrates is that in simulation and modeling, we do a lot of the vetting. But then the next phase of this is to really go implement it. So this is a controller. Siemens is a company that they've been using in the Chattanooga area. All of their controllers are Siemens M60 controllers. And we are fortunate to also work with Siemens on this project. That collaboration happened in the second year, and we have since worked with them. And right now we've been looking at a cyber physical implementation of these nicer and newer values, and have it a little bit more responsive, start getting into adaptive control of these. That said, the ecosystem that we have built allows us to look at a bunch of other things. I want to say that several projects have been funded in this area now. Minas RTP in the UT Chattanooga has a project that is very related to the C-twin work that we are doing. So we are partners in that. She has a test bed along the MLK Boulevard there, Martin Luther King Boulevard. A colleague of mine has a project now with Toyota, and I'm a co-PI on it. And there are aspects that we've built with C-twin that will facilitate that project as well. And in that project, we're beginning to look at all the way from the drivetrain to the intersection and the corridor, data driving that entire ecosystem of control. So there's a lot of things that are happening in this area that we are now poised to take advantage of and do something cool. In terms of demonstration of what this can do, we had found earlier that along the Shallowford Road corridor, we estimated that about 18% of energy reduction was possible in our simulation work. And then back in February, Kichao and several others, they worked on implementing an initial test of the values that we were getting using the existing software there. We call it the soft test. And having seen the outcome of that, we saw a 16% energy savings in the field. So we were exceptionally encouraged by seeing what we see in simulation and what we actually actualized. So that is why I say that 20% savings for a whole region is definitely doable. So on a follow on to that, this was an initial test of can we do things here. The collaboration with Siemens was maturing, and we worked to run a full field test in the last week of August. We ran this test Monday through Thursday. Thursday was, there was an accident on Thursday, and it's already made the experiment a little different on Thursday. But what you're seeing here, I think, has been a very interesting highlight. It took a while to get to the buildup of this, so there was a lot of vetting done to make sure that the NTCIP process of communication that Siemens has, we could use that and we could implement it well. Anne and Ki Chao and several others, they worked closely with the city to really define the detection zones that you see on the right. And then what you see again in the middle is the laptop I'm talking from right now and my monitor setup. But what I've done is basically remoted into a computer in our lab. This is all remote, working from home. And from that remote desktop, we were connected with the VPN tunnel into the city of Chattanooga, where we were executing the NTCIP and some control logic that we wrote on a virtual machine in their infrastructure, which was then connected to the controllers that are in the field. And so this is ORNL code, and these are the interfaces of the signal controllers, and here's some video that we were watching. But all of this was run completely virtually from our homes, and we executed 4 days of a control experiment in the city. We're still looking at the data. I don't have results for you right now, but just being able to do this and being able to do this remotely seems like we could write a paper on it. All of this really is getting to this integrated ecosystem of travel behavior and how travel is happening. So there's this decision aspect that's happening. There's the communication aspect of all of this. There's people driving all of the ITS and the activities, and the entire performance of this ecosystem then gets measured through the metrics. So that's what we're getting into now. Here's the next phase of our work. We're looking to really scale it up. The orange box you see in the middle, that's the existing extent of our work. But we are expanding it up along the I-24 corridor, hopefully get some of the data feeds that TDOT has been installing along I-24. Extend some towards Knoxville area, which is 75 this way. We definitely want to get more into Georgia and be able to capture some of the dynamics that are happening between Chattanooga and Atlanta, and then some along the I-59 towards Birmingham. All of this, we're going to have to rethink our data lake to be a little bit bigger. We have made some procurements. We have recently purchased some 400 gigabytes of space? No, 400 terabytes, sorry. So about half a petabyte of space we recently acquired and some compute around it. But on the data science side, we're beginning to look at things like traffic state prediction, incidents, of course, double down on that freight piece. We want to be able to take the signal performance that we have done on Shallowford Road, be able to really scale that up. Then, of course, with all this real-time data, we think we should be able to monitor the health of these sensors, which has a significant cost savings if we can tell them that, hey, these 3 sensors are not looking good, instead of having them to send someone to periodically check them. On the control side of things, we want to look at a few other things. Some of this could still be in simulation because infrastructure for ramp metering is not there. But we're looking to expand our signal corridor, signal control to take a corridor as well as a nearby interstate. This is not going to be like an integrated corridor management because ICMs are multiple millions of dollars. We're not at that scale, but we do want to look at what it might look like in that kind of environment. Then, of course, we are partnered with a number of fleets in the area, and we want to see and explore what we can do with fleet routing or optimization. And then, of course, there's this aspect of measurement and measuring the change. The logos that you see below here are all going to be partners in this next phase. the two labs on the left, NREL and Oak Ridge, the city, the Tennessee Department of Transportation. We have the public works of the city also working with us now, so that would give us some probe data. Georgia and data access from Georgia systems. We have a relationship with Abhishek, who's also at Vanderbilt, and he's got a project with CARTA, which is the Chattanooga Area Rapid Transit Authority. So there's some synergy there that we are exploring as well. We have a number of freight providers like Covenant Transport and Freight Waves working with us. Siemens has been working with us, and then our university partners, so UTK, UTC, and Vanderbilt. So all of this is beginning to gain some momentum, and we are quite excited about it. So with that, I'm going to stop. We have a few minutes for a couple of questions, I guess.
Thank you very much, Ibo, for very informative presentation. Very good. Actually, I have a bunch of questions, but due to time limit, maybe I'll just pick one or two out of it. For your digital twin, this kind of architecture, I noticed, if I understand correctly, most of those data stores that are coming from your edge, or from your physical entities, are infrastructure data, right? Do you consider any of the connected vehicle data as well, or maybe I'm missing that?
That's the focus of this next phase. We focus quite a bit on the infrastructure data. We had some initial discussions on connected vehicle data. We already had a pretty big pie, so we didn't focus too much on it, except for assessing the signal performance, where we were using connected vehicle data. This next phase, and I should say we use some TomTom data. We have some Waze data that we have used for looking at corridor scale things. We had some discussions with here, but I don't think we quite used it. And then we had probe data from ATRI. But this next phase is going to be significantly more of the connected vehicle data. So the public works has their entire fleet that's connected, and we expect that data to come in. We are expected connected vehicle data coming from the Georgia side of things as well. Covenant, which is a transportation company, they've got quite a bit of connected vehicle data in this area that they're willing to work with us on, as well as Freight Waves. Now, Freight Waves is a company that abstracts and encapsulates truck and trailer data from 4 other transportation companies. We are still working out through what should the NDAs look like, because some of this can expose which areas they actually run their lines. So we're working through that right now, so how to make sure that that proprietary information can be preserved. But yes, big time focus on connected vehicle data in the next phase.
And based on the NDA thing you just mentioned, so I assume this platform is not public available, right? There's no way for others to try it out if they're not the partners.
I think we should be able to get people logins. We need to clear that with our partners. So the NDA clause with the existing partners comes from us ensuring that there is a certain element of protection of some sensitive information or key information from these people. A lot of this data is quite open and available. The SmartWay data, TDOT data is fairly public. The city's data is not so public, but we haven't quite worked through if we need some fences and guards to make this open to people. I expect to have that chat with the folks, if I get such requests.
Got it. Thank you. And I think there are 3 more detailed questions in the chat box. Maybe after we finish, you can answer them one by one in the chat box. Due to time limit, we might move to our last presentation. But thank you very much, people.
Thank you. I want to say that I have a hard stop at this time, so I'm going to take a screenshot of the questions and I'll come back to them in 30 minutes.
Sounds great. Thank you. And I will contact you also for my questions. Thank you again. So let's move to our last but not least presenter, Meng Zhang. Meng, are you over there? Can you share your screen? Maybe you need to unmute yourself.
Yes, Mr. Wang, could you hear me now?
Yeah, I think I can hear you and I can see your slides. Great. So maybe you can do a short intro of yourself and then start your presentation. Thank you.
Okay, thank you. Good morning, good afternoon, or good evening. I am a PhD student in University de Montbéliard in France. My name is Zhang Meng, and I received my master degree, Control Theory and Engineering in Shanghai University in 2019. Now, my major is computer technology in the field of transportation. My research point is the relationship between intelligent vehicle and crossing pedestrians. Now, let me show you my research.
Meng, it seems like the sound is not coming through. It's not that clear.
It's not clear.
Yeah, maybe can you reshare your screen? So maybe I don't know. Maybe the computer audio is not coming through. Can you just replay? Let me check.
Okay.
Not on my side. Guoyuan, can you confirm?
Yeah, it's not also on my side. I'm wondering, when you try to share your screen, there's a box checking saying allow the computers like a sound or audio to be in. I don't know whether you check that box, because by default it's none check or uncheck.
How to share the sound in the video?
So maybe you can stop. You can stop sharing right now and then share again. When you click share your screen, there is a option at the bottom say you can share your computer audio.
Okay.
You can cancel the sharing right now and then do that one more time.
Okay, I see that. In industrial sites, based on trajectory optimization,
clear.
Vehicle signalization system. First, I introduce briefly the background of this research. As is shown in the picture, road space sharing is a complex decision-making problem, especially when the CAV conflicts with pedestrian traffic. Many factors should be considered. In the picture, the pedestrian won't cross the road, and there is a car. They must share this road resource. In such situation, two main contradictory factors must be studied. The first one is safety. That means no collision and low potential collision between road users, and another one is efficiency. We need to optimize the crossing time for both. As is shown in this picture, the study area of interest is unsignalized crosswalk without lights and zebra crossing. Second, control the longitudinal acceleration of CAV to achieve the balance of safety and efficiency. The third one, only one pedestrian in our scenario. The second part, we build the model for such problem. In this road, we define this area called conflict zone, CZ. CAV is coming at its desired speed, and also the pedestrian has a desired speed, VP hot. From time 0 to time t, we define several variables. D, V, U. They are traveled distance, speed, acceleration, and we also define a state space control variable, xt and ut. According to the definitions above, such a state space model can be easily constructed. And for considering of crossing efficiency for the agents, we give an objective function to minimize. That means the difference from desired speed. WP is the weight factor for pedestrian. We integrate squared value during the crossing and add it for cost function. And of course, we have some constraints for these variables. This is constraint for acceleration and for velocity. And for considering of safety, we define this function, and this one can keep that only one road users in the CZ at any time. This function can keep there is no collision. So finally, we can get the whole trajectory optimization problem. This is the state model and the cost function to minimize. Obviously, the last one is a nonlinear condition. The third part calculates the optimal trajectory. In order to obtain the optimal trajectory, we use a Hamiltonian analysis by using Hamiltonian optimization. Finally, we can get an important formula. This formula is the optimal speed for autonomous vehicle and for pedestrian. According to this formula, we can draw the speed curve of the leader and the follower. We noticed that the first accelerates to let the second cross sooner. Both behaviors are communicative. The leader agent accelerates first and show its intention to cross CZ first, and at the same time, the second one decelerates, meaning it gives the right of way to the leader to cross first. This is the optimal solution, but there is another important problem we have paid attention to. The human behavior is dynamic and adaptive. If the car is the follower, it must be able to stop if the pedestrian changed its speed. The car must keep that there is enough space to brake. TDF is the time of deceleration time for the follower obtained by solving the following equations. SC is safe condition. It can keep that there is no collision in the future. In the fourth part, this numerical example bolsters the behavior of the CAV by extending to 3 agents, 2 cars and 1 pedestrian. In the figure, if this car refuses the request of the pedestrian for safety reasons, it will send a message to tell CAV2. This car will prepare itself, if possible, to allow the pedestrian to cross earlier than itself. 2 scenarios tested. In scenario 1, the pedestrian cross in an ideal way in the optimal profile, and in the scenario 2, the pedestrian cross in an ideal way at the beginning, but he stops at 0.1 meters to the exit for testing if there is collision. Initial data is shown in table 1. The range for car acceleration is -3 to -2, and for pedestrian -1 to 1. Initial distance for the first car is 46 meters, and the weight for pedestrian in objective function, we set it to 20. This is the result for scenario 1, and this is the same with the optimal solution. They cooperate with each other to crossing the zone. And in table 2, here is the comparison between the optimal trajectories and the spontaneous one. And in this table, we can see, especially for CAV2, the cost spontaneous way is very, very high, and the crossing time is longer. Hamiltonian optimization obviously is effective and also efficient. In scenario 2, after the first car crossing, the pedestrian enter the zone and stop in the zone. In the result, the final space between car and CZ is about 2.2 meters, so there is no collision. And during the crossing, the pedestrian here changed its speed. The vehicle also adjusts its speed to keep safety. The optimized speed control could achieve minimum cost for both. Finally, we performed a series of experiments using mixed reality platform. The platform is based on Oculus Quest. For exploring better communicative behaviors, we added a signal in front of the car to show the decision of itself. A child tested 2 scenarios, as in the picture, without a signal, and here with a signal for better communicative behaviors. Compared with the first experiment, the second used the proposed interaction behavior, and the curve shows that the pedestrian waiting time before crossing is much more shorter. This is because the method proposed in this article enables pedestrians to know the intention of the car earlier. The red light means stop, and the green means the pedestrian go first. In addition, observing the curve of the second experiment, the car continuously adjusts its speed according to the state of the pedestrian and achieve the purpose of passing CZ in the shortest time under the conditions of safety and acceleration limits. Finally, let me show you the 3D simulation from third-person view. Here, the cube represents a pedestrian when he approaches the road. Red light, so we cannot go. And at the same time, the second car prepare it, so I can cross before the second car. Again, red light, I should wait. We test if there is collision. I stop there. So that's all of my presentation. Thank you very much.
Thank you very much, Mon.
Thank you.
I haven't seen you share your email address. Can you share that with us, just in case anyone have some offline question for you?
Email? Yes.
Yeah.
Yes, I can. I can show you from IV. Yes, this one is
So
the recent email, October
okay, I see.
25.
So your email, I mean, your email address is meng.zhang@ciad or something.
Yes, here.
Yeah. I mean, to share your email for the attendees, just in case anyone. Okay. I see.
Okay.
utpm.fr. So
yes.
Yeah, thank you. And I think we have a question for you at the end of this. In your optimization, you also calculate the optimal trajectory for pedestrian, right?
Yes.
Or just for the vehicle?
For both. Here we calculated and get the optimal trajectory for both. But here is a problem that usually the pedestrian sometimes rational, but sometimes perhaps for any reasons he stop in the road. So so this curve is a kind of reference.
Mm-hmm.
So,
okay, I see.
And yes, we add this condition for the safety reason. If the pedestrian cross just like the optimal curve, the car will behave like this. So we want to optimize the whole system.
And is there any speed guidance for the VR? So I guess that the pedestrians is wearing the VR, right? Is there any speed guidance or just the green or red indication for go and stop?
Sorry, could you please repeat your question?
Yeah, so for the VR for the pedestrian to cross intersection, we saw the red and green light for indication, right?
Yes.
Is there any other information like speed guidance or detailed information, or just the green or red lights?
Not yet, just the red light. This is the only signal between pedestrian and the vehicle. And we know that from previous research, the pedestrian can get information according to the speed and the acceleration rate of the vehicle. So we add this signal. It can help decrease the reaction time of the pedestrian.
I see. So last question, actually related to this one as well. Did you consider how to determine the presence of pedestrian and their intention to cross? So how do you predict the behavior of pedestrians?
Yes. In our research, we didn't consider the detection of the pedestrian. So in the experiment, I set a boundary here. Just if the pedestrian enter the boundary, and the car will use this control algorithm.
Got it. Okay. Thank you very much, and thank you for your presentation and for the questions from the attendees. And if you have any more questions for Meng, please feel free to send to the email that he just showed earlier. Yeah, thank you, Meng.
Thank you.
And I think this concludes our full session. And this is my expectation, right? Last time we have a workshop on Saturday, and that day we have more attendees because maybe other people, they might have no meetings during Saturday, but on Friday, people seems to be more busier. But today we also have a lot of engaging discussions, which is really good. So later I will share our video recording to all of you, and also the chat information, the history of the chat, the Q&A to all of you. Guowen, do you have any words you want to say?
No, excellent. Yeah, and also as Zhan said, we really appreciate all the presenters and also all the audience to attend the whole session. Thank you.
Yeah, thank you, everyone. I hope you have a nice day. Bye, everyone.
Thank you. Bye.